unlimited potential, and with the right education and encouragement, they can even move mountains. He believes that learning is the beginning of spirituality, and if we can inculcate the rich Indian values, heritage, and age-old tradition infused in science, a flawless character can be developed. We are blessed to receive his continuous support and guidance.
Sustainable chemistry is a scientific concept that seeks to improve the efficiency with which natural resources are used to meet human needs for chemical products and services. And this lecture workshop, Chemistry for a Sustainable Future, intends to cover emerging topics like nanochemistry, protein chemistry, environment, green chemistry, energy and healthcare applications, utility of fluorescence spectroscopy in chemistry and biology, and green hydrogen as future fuel, which will benefit the students, researcher, and the faculty.
Along with the lecture session, the hands-on experiment session will also help the participant learn the principle of chemistry through simple experiments.
For the workshop, we have with us as the convener and resource person, Professor A.K. Ganguly, who currently holds the Professor N.K. Jha Chair in the Department of Chemistry, IIT Delhi. He is also the Joint Professor in Department of Material Sciences and Amplifiers and Deputy Director Strategy and Planning at IIT Delhi. He is the founding director of Institute of Nanoscience and Technology in Mohali. Professor Ganguly obtained his PhD from Solid State and Structural Chemistry Unit, SSCU of Indian Institute of Science, Bangalore, in 1990, in the area of thallium-based high-temperature superconductors, for which he got the Sedborough Medal of Indian Institute of Science. He has been a visiting scientist at DuPont Company, USA, and a postdoctoral associate and visiting scientist at Ames Laboratory, Iowa State University, USA, and visiting professor EPFL, Lausanne. His areas of interest are in the design of nanostructured materials for applications in water purification, solar energy conversion, and microfluidic devices, and also high temperature superconductivity. He is a recipient of the National Award of Nanoscience and Nanotechnology given by DST, the Chemical Research Society of India, CRSI, Material Research Society of India, MRSI Medal, the CNR Rao CRSI National Award, Chemical Excellence Award by Indian Society of Chemists and Biologists, and the Bangalore India Nano Award by Karnataka Government. He is a Fellow of Royal Society of Chemistry, London, Indian Academy of Sciences, the National Academy of Sciences, India, and the Asia Pacific Association of Materials. He is currently an Associate Editor of Bulletin of Material Science and Member Editorial Board, Journal of Indian Chemical Society, ACS Matter LETS, and Chemical Physics. In an outreach program by LETS at INST Mohali for rural school students in remote parts of India, he has visited more than 300 schools, and in the last 3.5 years, he has created several programs involving a large number of students all over India. It is an honor and privilege to have you among us today. I would now request Director Modi University, Professor Rajiv Mathur, to welcome Professor A.K. Ganguly with the bouquet. Thank you, sir.
Ladies and gentlemen, we also have with us today Professor Uday Maitra from Indian Institute of Science, Bangalore. Professor Uday Maitra completed his MSc from IIT Kanpur in 1981 and obtained PhD from Columbia University, New York in the year 1986. He has been the postdoctoral research associate at University of California, Berkeley from 1986 to 1987. He has several awards to his credits like Fellow of the Indian National Science Academy, J.C. Bose National Fellowship, S.S. Bhatnagar Prize in Chemical Sciences, Fellow of the Indian Academy of Sciences, etc. Professor Maitra is the member, International Advisory Board for the Chemical Society Reviews. He is an editorial board member for the Asian Journal of Organic Chemistry, member, American Chemical Society, Royal Society of Chemistry, National Representative, IUPAC Committee on Chemical Education, etc. We are blessed by the presence of such a great scholar among us today. I would now request Dean School of Liberal Arts and Sciences, Professor Jitendra Binwal, to welcome Professor Uday Maitra sir with a bouquet. Thank you, sir.
Ladies and gentlemen, for the workshop we also have with us Professor Ramakant from University of Delhi. Professor Ramakant did his BSc and MSc in Physical Chemistry from University of Delhi. He obtained his PhD from the Department of Inorganic and Physical Chemistry, Indian Institute of Science, Bangalore. He was awarded Dr. Srinivasa Rao Krishnamurthy Best Thesis Medal in the area of electrochemistry and electrochemical engineering for the year 1994 to 95. His postdoctoral research training was done under the guidance of a Nobel laureate, late Professor P.G. de Gem at Collège de France, Paris, and another postdoctoral research with Professor T.C.B. MacLeish, FRS, at University of Leeds in the area of polymer physics. He is the recipient of many international fellowships, namely EPSRC Britain Fellowship, Ministry of Foreign Affairs France Fellowship, University of Freiburg, Germany Fellowship, etc. Professor Ramakant joined Department of Chemistry, University of Delhi in 2003, and his research interests include the development of theories, simulations, and experiments of complex systems in electrochemistry and polymer. Professor Ramakant has pioneered and extensively developed difficult research areas of theories for the electrochemistry on rough, porous, and heterogeneous electrodes. His significant contributions are derivation of more than 60 fundamental and novel equations for electrochemistry of disordered atomic and nano scale and nanostructure electrodes, which led to the generalization of several well-known classical equations in fundamental electrochemistry. His contribution to knowledge has led to the fundamental understanding of dynamics of electric double layer and electrode kinetics of rough and fractal electrodes, and their transient responses like chronoamperometry, impedance chronocoulometry, chronoabsorptiometry, pulse voltammetris, and admittance voltammetry. Recently, he has developed novel modular theoretical approach for the impedance spectroscopy of complex electrochemical systems and devices. Professor Ramakant is elected as a Fellow of Indian Academy of Sciences, awarded CRSI Bronze Medal and Acharya J.C. Ghosh Memorial Medal in recognition of his contributions to fundamental electrochemistry. We are honored by your presence, sir. A warm welcome to you. I would now request Professor A.K. Das to welcome Professor Ramakant, sir, with a bouquet. Thank you, sir.
We also have with us today Professor Parbati Biswas from Department of Chemistry, University of Delhi. Professor Parbati Biswas obtained her PhD from Indian Institute of Science, Bangalore in 1996, and her field of specialization is theoretical physical chemistry. She has diverse postdoctoral experiences which included a brief stint at the Department of Physics and Astronomy in the University of Leeds with Professor T.C.B. MacLeish as an EPSRC Fellow. She received the Alexander von Humboldt Fellowship and worked on the various problems in polymer physics at the Department of Theoretische Polymer Physik, University of Freiburg, Germany. Subsequently, she worked as a postdoctoral research associate in the Department of Chemistry, University of Pennsylvania, USA, on protein folding and design of later joined Department of Chemical and Biological Engineering, Rensselaer Polytechnic Institute, USA, to work on molecular dynamics of protein splicing. Her research interest includes statistical theory of protein folding, misfolding, and combinatorial protein design, statistical mechanics and molecular dynamic simulation of biopolymers such as protein, DNA, and membranes, dynamics of branch polymer and polymer network, and rheology of complex fluids. She received Professor S.K. Chatterjee Award from Indian Institute of Science in 2016 and Charusita Chakravarti Memorial Lecture Award of the Chemical Research Society of India in 2017. It is an honor for us to have such a profound woman among us today. A warm welcome to you, ma'am. I would now request Dr. Sarita Katuria to welcome Professor Parbati Biswas with a bouquet. Thank you, ma'am.
Ladies and gentlemen, we also have with us today Dr. Soban Singh from the School of Physical Sciences, Jawaharlal Nehru University. Dr. Soban Singh completed his PhD from Indian Association for Cultivation of Science, Kolkata. He has been postdoctoral fellow at Department of Chemistry and Biochemistry, University of South Carolina, USA, and also JSPS postdoctoral fellow at Molecular Spectroscopy Laboratory, RIKEN, Waco, Saitama, Japan. His areas of specialization are ultra-fast and single molecule fluorescence spectroscopy, molecular dynamics simulation, biomolecular dynamics. A warm welcome to you, sir. We are honored to have you with us today. I now request Professor Harlal Singh to welcome Dr. Soban Singh with a bouquet. Thank you, sir.
A warm welcome to all. I would now like to invite Professor Jitendra Binwal, Dean, School of Liberal Arts and Sciences, for his welcome address.
Namaskar. Good morning to all of you. As a Dean, School of Liberal Arts and Sciences, I welcome you all. Good morning, one and all present here. Honorable Director Sir, respected invited speakers and other dignitaries and dear participants. Today's lecture workshop on chemistry for a sustainable future is being organized by the Department of Chemistry, School of Liberal Arts and Sciences, Modi University of Science and Technology. This workshop would serve as a common platform for participants of experts from industry, academia and research organization, and would provide a knowledge sharing pedestal to have an insight into the current scenario and technological advancement in their concerned fields. Modi University of Science and Technology, exclusively women university, which has been created with a vision to promote environment for advanced education for female population in the state of Rajasthan. Science Academies lecture workshop is an important segment of the activities under the Science Academies program, that is SEP. The lecture workshop is intended to benefit students and research at the undergraduate, graduate, postgraduate and research levels in this remote and underprivileged area. The workshop has been designed to have relevance to the curriculum covered in the postgraduate, graduate and undergraduate programs, and it also covers some topics at the research levels. This workshop will motivate participants and enable them to understand and apply chemistry for application in energy, environment and healthcare. I would like to especially thank the convener of the lecture workshop, Professor Ashok K. Ganguly sir, FSc, Fellow of Indian Academy of Science, Fellow of National Academy of Science, Department of Chemistry, Indian Institute of Technology, Delhi. I am also thankful to the coordinator, Professor Dr. Amlan Kumar Das, Department of Chemistry, School of Liberal Arts and Sciences, Modi University of Science and Technology. There will be total of 10 lectures, cover 2 days workshop, which are related to relevant topics, just like nanochemistry, chemistry for central science, a world without chemists, the chemistry world of tomorrow, green chemistry, polymer and protein chemistry, environmental, energy and healthcare applications. I also would like to thank all the invited speakers, Professor K. Ganguly sir, convener of this workshop, Professor Uday Mehta sir, Professor Ramakant sir, Professor Prabhavati Viswas ma'am, and Dr. Sen sir from JNU. I would also like to thank all the three academies body for sponsoring this chemistry lecture workshop, the Indian Academy of Science, Bangalore, the Indian National Science Academy, New Delhi, the National Academy of Science, India, Prayagraj. I'm sure that this workshop will be very much helpful and beneficial to all the participants, and I'm also thankful to our Honorable Chairman sir, management and our Director sir, and I think this workshop will play an impetus role with the coordination of this NAP and what is the role of the chemistry at present scenario, and without chemistry research is not possible. With this theme, again I welcome you all. Thank you very much. Namaskar.
Thank you, sir. Now, I request Professor Ashok Kumar Ganguly, the convener of workshop, for his address.
Good morning, everybody. It's wonderful to be here. I've been here several times, and very happy to see that this university has grown in stature, and many of their alumni I have met in other institutions. So I'm very happy to be here. My voice is not great. The weather was not great past 2-3 days in Delhi and also here. But you know, I have always loved to come here. I think we are doing this is probably the third science, I don't remember, at least fourth Science Academies meet here, and 2 meetings we did something else, and the management has been very positive, and the directors, deans, and of course Amlan Das has been the Sutradhar for most of the events here. So please give him a big hand. And I must tell you, the speakers you will hear are all outstanding. Everybody knows them in India. If you go to any of the top institutions of our country, as students you should know. If you go to IIT Kanpur, IIT Bombay, everybody knows everybody. All these names which you are hearing will be known everywhere in India. If you go to TIFR, everybody knows. So you are going to have a feast of great science or technology, although they will be talking at a lower level than at the real research level, because they want you to enjoy what good science brings out. And you know, nothing, I give a talk to many outreach lectures that साइंस ने क्या किया है हमारे लिए. तो आपके आसपास जो भी है, आप जो शर्ट पहनते हो उसके बटन्स भी नहीं थे. वो बटन्स भी किसी साइंटिस्ट ने बनाए थे पहली बार 1000 साल पहले, 800 साल पहले, 500 साल पहले. Right? So science is very modern. In 200 years we have traveled from bullock carts to now we can go to we are planning to go to the Mars. Right? People are planning human landing on Mars now. Moon has been done 50 years back, right? So that's where technology is only 200 साल. एक यूनिवर्स के लाइफ टाइम में 200 साल क्या होते हैं? कुछ भी नहीं होते हैं. We are 4.5 billion years old, right? That's the age of our universe, so called. And उसमें 200 साल में आपने इतनी तरक्की करी है, तो अगले 200 साल में आप क्या नहीं करेंगे? So you are all children of that 200 साल. आप देखोगे अगले 30 साल में the way robotics and artificial intelligence will come. You will enter into stores. Already there are stores in certain countries, unmanned stores. आप अंदर जाओ और सामान उठा के ले जाओ. Your card will be automatically, the moment you enter the store, all the information will go to a central computer. And automatically, the moment you pick up this box, that box, it will start deducting from your account which is joined. So that is already done today. So the world is going to be very, very different in the next 20, 30 years. And you will all grow up. Many of us may not see in 20, 30 years what will happen, but you will all see that. So all that science and technology has to grow somewhere from some fundamentals. So many of those fundamentals we have to see. But the topic of today is very important because you cannot close your eye to technology only. Open your eye to technology only and close your eye to environment because you have only very limited space. So far as we know, this is the only planet where humans are alive, right? And this planet is very small. Now our population has now grown that animals are becoming extinct and plants are getting extinct. You can see pictures of animal activists showing थोड़े से ice patch पे 4 polar bear बैठे हैं. They don't have space to move. If you go to all our Antarctica and Arctic Circle are shrinking. If things are not taken, we'll talk some of those things today in my talk. How many countries will go into water within next 20 years? Countries पानी में जाएंगे, right? So you have to do now responsible technology. That's the next thing. You just cannot make any material without thinking इसका by product क्या होगा, ये material को कैसे waste management करना है. You will not be able to. The fine will be so much. अभी आपके ऊपर नहीं आया है, पहले दिल्ली, बॉम्बे, हैदराबाद, बैंगलोर पे आएगा. You will have tremendous taxes on you to drive a car. So minimize people from driving. Many such things will come. They came in many countries earlier, in Netherlands, Sweden, Norway. Very strict laws. So if you go to Norway or Netherlands, you can find ministers जो cycle पे office जा रहे हैं. I have traveled with the Swiss Prime Minister in a train, going from one place to another. He was going to office. So there are many things like that we will have to follow. We are a huge population. आधे population के पास तो अभी पानी भी नहीं है ढंग का and light भी नहीं है. उनको वो improve करना है, तो some of the others have to curtail their aims of luxury, having 4 cars, things like that. You have to also look at the car that you buy. How much is the efficiency of that car? Thank you very much.
Thank you, sir. Now, I request Dr. Sarita Katuria, Head of the Department, for her address on role of chemistry in sustainable future.
Good morning to everyone present here. Honorable Professor A.K. Ganguly sir, convener of 2 days workshop. Professor Rajiv Mathur sir, Director of Modi University and patron of workshop. Professor Jitendra Binwal sir, Dean School of Liberal Arts and Sciences and Chairman of the workshop. All the distinguished speakers, Professor Uday Mitra sir from IISc Bangalore, Professor Ramakant sir and Professor Parvati Bishwas from Delhi University, Dr. Sobham Sen from JNU, all the participants, faculty members and staff members, and my dear students. I, Dr. Sarita Katuria, Head Department of Chemistry, on behalf of School of Liberal Arts and Sciences, welcome you all in these 2 days lecture workshop, that is Chemistry for a Sustainable Future, which is an emerging topic in current scenario. sustainable future or sustainability means fulfilling the needs of current generation without compromising the future needs of future generation. It means we have to make a balance between economic growth, environmental care, and social well-being. Chemical researchers are continuously working on the development of earth-abundant advanced materials for renewable energy production and energy storage solution. Chemistry offers new solution for reducing pollution and its impact on human health. Chemistry provides a deeper understanding of how human health is impacted by disease and hazardous chemicals in our food, water, and environment. Chemistry plays a critical role in medical diagnosis and drug development. During COVID-19, we all have seen that understanding of viral structure, its mechanism, pathogenesis, isolation of vaccines and therapies all become possible by the knowledge of chemistry. We can improve the water quality by deployment of greener technologies which will benefit the entire planet surely. Green chemistry is also known as sustainable chemistry, which helps to save and conserve resources and protects our health and environment. In our department in chemistry laboratory, we are working under the framework of green chemistry and we are continuously synthesizing bioactive heterocyclic compounds like spirondoles, benzopyranes, pyranopyrazoles and bigenally compounds. We are also synthesizing shift-based metal complexes and we are also performing the green synthesis of nanoparticles. It means we are synthesizing nanoparticles by using renewable plant extracts, orange peel extracts, green tea, aloe vera extract. All these are the renewable resources. So we can say that we are working under the framework of green chemistry. And we, in our department, we have microwave, centrifugation, UV spectrophotometer, sonicator, infrared spectrophotometer for synthesis and initial characterization. Recently, we got Curie fund and we will soon we are going to order advanced instruments for their synthesis and characterization and biological evaluation also. We have undergraduate, postgraduate and research laboratories in our department. At present, 5 students are pursuing PhD and 4 are doing dissertation in chemistry laboratory. Tomorrow, a laboratory visit is planned for all the delegates. Thank you to all the delegates for bringing their expertise and experience into this 2 days lecture workshop. One more thing, this year 2023 is announced to be International Year of Basic Science for Sustainable Development. Without any further delay, now I welcome you all once again in this 2 days workshop and hope that all will have a great time ahead. Wishing all the participants for their active participation so that this workshop becomes fruitful and constructive. Thank you very much.
Thank you, ma'am. Now I request Professor Rajiv Mathur, Director, Modi University of Science and Technology, for his address.
Good morning, everyone. Respected invited speakers and other dignitaries, dear faculties, students and participants. First, I'd like to welcome all of you on behalf of our chairman, Shri R.P. Modi Sahab. And I'll really thankful to Binwal sir and Amlan Das ji, who has taken this initiative. And I'm highest thankful to the 2 students who gave us detailed introduction of all the 5 mentors coming to this place, because it is only after hearing the complete details we all fall in love with you, sir, and we all are looking forward to listen to you. So I'm really thankful to those two, and I really appreciate that it goes unsaid that what kind of hectic schedule you guys must be having, but you bothered to come all the way to this place, because I can very well understand coming to Lakshmangarh is a tedious job. Is from Bangalore, from Delhi, so I'm really thankful to all of you, and I welcome all of you on behalf of our chairman, management committee members, faculty and students. Chemistry for a sustainable future, as sir said, that we should have responsible technology. It is very important. Since tomorrow morning, I am getting a lot of videos coming from various parts of Rajasthan. People are enjoying playing with snow in the Mewar region of Rajasthan. Now, this is a very horrifying scene, because I don't appreciate the faces of the people who are enjoying the snowballs and all. What I foresee is what we have done and what we are leading to. Out of the many factors responsible for this, science is a major part of it, sir, because the development has costed a lot. But it's very good that now we are talking in terms of sustainable future. Now we are talking in terms of responsibility of science towards environment. Now we are talking in terms of this, that any other further development will not cost anything to the environment. So that is a wonderful future, and that's the amazing thing that we'll be talking about this for the next 2 days. Because having a snowfall in Rajasthan and having a picture where 4 reindeers are sitting on a small patch of snow, these are the horror scenes, and not only for us, and even worse for the coming future, for the coming generation. So we have to be very careful for that, and we have gone for a topic covering this. That is a wonderful idea. Made it relevant with yesterday's weather. So I welcome all of you. Thank you so much, sir. Thank you, ma'am. Thank you so much.
Thank you, sir. I request you all to join us on the stage for a group photograph.
All participants and faculty members, please join us for the group photograph.
Thank you. I request you all to join us for high tea to be served outside the Sabhaghar at Bharat Muni Manch. I also request you all to take your seats back in 20 minutes for the workshop. Thank you.
morning and welcome back for the first session. So, many of you must be thinking, what is this green hydrogen? In school, we are taught hydrogen is a colorless gas. Right? Hydrogen, as you know, in the periodic table, it's the first element in the periodic table, right? So it's a very light atom. Okay. So that's very important. H2 is a very light gas. It has a lot of energy. So light and giving lot of energy is very important. The second thing is hydrogen, when it burns in oxygen, it gives water. So that's again very nice. You are getting water, which is a very good product. You don't have to worry about any product formation, which is not going to spoil the environment. It's good. It can be reutilized. So that's why hydrogen as a fuel is very, very important. Unfortunately, hydrogen in the earth, the abundance is like hydrogen availability is always with some carbon. So free hydrogen is available, the amount is less. So mostly we generate hydrogen from hydrocarbons, right? So deep inside the earth, we have petrochemicals. And when we dig out petrochemicals, then we break it down into many smaller fractions of hydrocarbons, and then we have processes by which we can make hydrogen from hydrocarbons. So this the gasification process is very important in chemical engineering, where how you make hydrogen from hydrocarbons has been done for several years, and the technology is very well developed. But that is going to give you carbon dioxide along with hydrogen. So the aim now the world wants, can we have hydrogen without carbon being added to the atmosphere? So we must be able to take out or absorb the carbon which is coming out as carbon dioxide or carbon monoxide, in some cases as carbon. We need to absorb it or convert that into something which is useful. What is the problem with having carbon dioxide? So all of you must have studied that if you have carbon dioxide, we create in the atmosphere something, ozone hole, etc. Right? So the atmosphere will, if we have this kind of heating because of some carbon-based gases, the temperature of the earth will rise. This is a problem. That's why we don't want carbon dioxide excess in the atmosphere. There was a Paris Accord which 196 countries signed, where they said that we have to bring down the carbon content, and every country has to contribute. Otherwise, you will have to pay a fine. So India is also a signatory to the Paris Accord that was signed in 2015, because 2 countries have come out of it. We now have 194 countries in that accord. Every year there is a meeting. So in that accord, it mentions what all things you have to do, what are the steps that you have to do. And every year somebody is monitoring, did India take these steps? Did US take these steps? If you don't take certain steps, you will be fined. So you will have to pay. So there are now things like that in the world, and that is why do you think suddenly in the newspaper so much is coming about electric vehicles, electric mobility? because that is one thing you have been told to do. You have to enhance those things, right? So that's why the government of India has to put those. That's why in cities like Delhi, we already have chargers on the road. We have chargers in certain locations. That will keep increasing. On certain highways, you will have chargers so you can drive electric vehicles. But every city does not have that. Every highway doesn't have that. To do chargers, you must have electric car. How many of people have bought electric vehicles? So government subsidizes. Today, if you buy an electric vehicle, I think there is some subsidy. These are all steps in the Paris Accord, ultimately to reduce carbon footprint. So you will be hearing these words as you grow up. And if you want to be in areas where you make a difference, that means you can study any subject. But are you in a subject which the world is working on? So you have to think of this kind of thing. Do you know the term what is carbon footprint? Do you know what is called carbon payback or carbon penalty? Do you know what is sustainability? These are the terms. If you are in these areas, working in these areas, then the world has jobs. United Nations has jobs. You will be part of some organization, some think tank who is monitoring this, who knows how to do statistics. So in future, sustainability is a great thing. Right now it's a great thing, but as future grows, it will become a great thing. So green hydrogen, the color of hydrogen is not green. And what do we mean by green hydrogen? Green hydrogen means the process by which we are making hydrogen should be not producing any carbon footprint. We must have a cycle to absorb any carbon or carbon dioxide, carbon monoxide by the process of breakdown of hydrocarbons into hydrogen. We must have a process to utilize that carbon. Then you will get green. So plants make fuel from solar energy and water. In the plants, you have the chlorophyll, right? The chlorophyll is a pigment, and chlorophyll is actually a metal porphyrin complex. If you study chemistry, we study in bioinorganic chemistry, right? What is bioinorganic chemistry? Inorganic chemistry in living processes. Those living processes may be in plants, it may be in the human body. So one example all of you should know is bioinorganic chemistry in your body is how your RBC, red blood corpuscles, pick up oxygen, right? You are breathing oxygen, right? Oxygen has to go to the lungs, right? How does it go? It's captured by the hemoglobin, right? It becomes oxyhemoglobin. And then it goes and delivers the oxygen to the muscle where it is stored in the myoglobin, right? So this is all chemistry. Without this, none of us would be alive. That's why chemistry is important. You need to understand, as I'm talking, I'm breathing in oxygen and I'm breathing out carbon dioxide, right? So how does that happen? Bioinorganic chemistry. Of course, I can also do physical chemistry because you have to understand the oxygen attaches to the iron in the metal porphyrin. What happens to the iron? The oxidation state is changing. How do we study this change? We can study by many techniques. We can study by EPR spectroscopy. We can study Mossbar spectroscopy. All that we study in chemistry and physics. All that has been done 40 years, 50 years back. We understand the mechanism very well. When myoglobin happens, what happens to the protein which is associated with that in the hemoglobin? What happens to the amino acid which is histidine? Right? You have read amino acids, glycine, alanine and all these. So there is a histidine amino acid which binds. When that happens, it pulls, there is some changes in the protein that causes a lot of things. That's how you should read chemistry. Understand, connect your chemistry to real life processes. Similarly, when plants make fuel from water and sun, this is the chemistry. This is something called photosystem 1 and photosystem 2. Two systems across a membrane. These reactions are happening in the plant, the chloroplast. When it captures solar energy, so photon is captured. Photon will give some holes and electrons, And light, what are the parts? What does light make of? Light is made of photons. What are photons? It's a quantized particle which has no charge and no mass. If you break a photon, what will you get? You'll get an electron and you'll get a hole. What is hole in physics? Is absence of electron. A hole has the same charge as an electron, but positive. Okay? Right? It is the same mass. An electron and a hole combined, they'll give light, a photon back. So from photon in the plant, when it captures, it creates electrons and holes. It splits the photon. That electron and hole goes through photosystem 1 and 2, and there is a beautiful process. If you study chemistry and biochemistry, you'll understand how these processes are linked and at what time scales. That's when you do ultra-fast spectroscopy, which Sobensen will tell you how fast a process is happening, how fast the electron is moving from one state to another. It's not second, it's not microsecond, it's a nanosecond, picosecond. Some process may be femtosecond, right? What is femtosecond? 10 to the power minus 15 of a second, right? So all these processes plants can do at room temperature. Can we do such things at room temperature, right? And efficiently. Then we can do the same things in the lab. Unfortunately, we cannot do very efficiently. Of course, plants also are not very efficient, but there are lots of plants and lots of leaves, so they can do sufficient amount of energy conversion. So what are we talking about? We're talking of energy conversion from solar to plants are converting solar energy into fuel. That is one part of chemistry we teach today. Solar energy to fuel, right? They make sucrose, right, which is energy. We want to make solar energy to hydrogen, another fuel, which we can put it in our car and run our car. So solar energy can convert to fuel, the plant does, we can also do. For us, we also want to make hydrogen and run vehicles on hydrogen. What is the world using energy today? So if you look at how much percentage of energy is used, 32% is used for, say, domestic purposes, and 25% is being used for, 32 I think is transport, 25 is domestic, and 35 is industry. These are the three major components, the world's use of energy, right? So the world's use of energy, if you can calculate, it may be in terawatts. But you understand what a terawatts, 10 to the power 12 watts or something. Do you know how much the sun gives us energy? Why sun is so great? In 1 hour, if I can capture all the photons which are coming from the sun, I can make the whole world run for 1 year. If I can capture all the photons coming from the sun, 1 hour of sun, if I can capture all the photons, I can convert to electricity which can power the whole world for 1 year. But we don't have technology to capture all the photons. That's the problem. Okay? But you see, where is energy going to be used? Domestic, industrial, and transport. These are three major. Of course, you have other areas where energy is being used. Where is this energy coming from today? If you can see, right, so a large amount is black and gray, right? Black and gray is something the whole world has been using for a long time. That is coal and other natural gas. So coal, natural gas, these are called fossil fuels. Why are they called fossil fuels? They have taken thousands and millions of years to become coal, right? Over time, they have turned into coal, right? So that is why they are called fossil fuels. But what we want actually is this green part to grow. You see, from 2012 to what is projected for 2040, the growth is 100%. Say now we have around 5 trillion kilowatts in 2010, and this is probably 10 trillion. So only 5 to 10. In 30 years we are going to just double. But the amount required is something like 35 trillion. Where will the rest of the 25 trillion kilowatts come from? It's coming from natural gas, something like 15 trillion. That's going to produce all the carbon dioxide in the air. Can't afford that. If we do that, we'll all die, because that will raise the temperature of the world by 2 degrees centigrade by 2100. Do you understand 2 degrees centigrade? 2 degrees centigrade will kill so many amphibious animals in the polar ice caps, like penguins, walrus, polar bears, etc. 2 degrees centigrade, maybe 10, 20 countries will go underwater, like Bangladesh, etc. Part of India will go underwater. Many of the islands, Mauritius, Maldives, everything will go underwater, because the ice caps will melt. You watch any National Geographic movie on ice caps today, and they have pictures taken 50 years back and today, and you will see the ice caps have shrunk. Earlier so much ice cap, now we have this much. How it is shrinking. So you need to increase this green part, right, or the yellow part, which is nuclear. But people are a little bit scared about nuclear. But many countries like France and Canada and Australia, they have huge nuclear energy coming. India also has a little bit of nuclear power, but it is very less, because you need very good safety for nuclear reactors, etc. So that's another thing which one has to see. So my point is, even with so much information in the world, even with now all the countries, 194 countries out of 200 some countries have signed, but still actually now it is going out of our hand. It's not in human beings' hand, because at the rate at which you are trying to control is not good enough. We still will have an increase in temperature. That's what I will show you. What are our hydrogen energy sources? So as I said, we can anything. Solar is the best, because we have so much solar, especially Rajasthan, right? So places like Saharan Africa, Rajasthan, all that near the equator countries, part of Australia, which has a lot of sunshine, and you need open places, like Rajasthan has a lot of open. You have to put solar panels. The problem with solar is you need solar panels to be employed, so you need a lot of open area. You need thousands of kilometers of open space to put your panels. Like we now encourage people to put solar panels on every rooftop in the city. So entire IIT Delhi, all our roof, top floor is covered with solar panels. It's a part of the mandate. Now in many of the cities, you cannot build a house. Your plan will not be passed by the local administration unless you show how much power you are generating from solar. So in many cities, I have friends in Bangalore who have reactors, water heaters. So solar to water heater is a very easy technology. You can buy it, it's very cheap. You can convert. But solar, to convert electricity to put power into your television is slightly more you sophisticated. You have to spend a little bit more money. So all this, the government is going to put more and more pressure, especially in cities where there are people who can pay more taxes, will pay more money. So they'll charge them with heavy duty because they are going to apply. Every new building in Delhi has to have solar power generation. Okay, and now every building recently has to have electric chargers in the basement. In my flat building also, we have an electric charger in the basement. Becoming mandatory now. Any new building, you need to have a charger in the basement. So you can have hydrogen from solar, from wind. Again, wind you cannot have everywhere because you need wind intensity has to be in open places. Again, Rajasthan is a good place, or on the seashore. So Gujarat has a lot of windmills. If you go to Gujarat, all along the coast, Odisha is a good place for windmills. But the energy conversion, you will see in percentages, is not too high. But everything counts. You add together all these percentages and it counts. Biomass is something. So from biomass, you can get hydrogen, right? But you have to take out, if there is any carbonaceous thing, that has to be absorbed. Otherwise, this process will not be allowed now. You have to have a process from biomass if you are generating hydrogen. The carbon waste, whatever is coming out, you need another technology parallelly to convert it to a valuable product. Okay, of course, you can use hydroelectric power, etc. There are other sources to get hydrogen. Now, color of hydrogen. So as I said, we want green hydrogen. Gray hydrogen or black hydrogen, the more carbon content in the process used to produce hydrogen, the more gray or black it is. Okay. Now, if you have yellow hydrogen, pink hydrogen, that means you are somewhere in the middle. It's not very bad as gray hydrogen or black hydrogen, and it's not so good as green hydrogen. Green hydrogen means no carbon in the atmosphere, purest form. Only hydrogen, no carbon. That is through renewables you are producing, like wind power, or through solar energy, you are getting the hydrogen. So these are the colors. So this is traditional method of getting hydrogen from natural gas, coal or lignite, and they will give you brown and gray hydrogen, etc. And the process is developed by chemical engineers long back, is a gasification project which produces maximum amount of hydrogen anywhere in the world is by that process of gasification. Okay, but it will give you carbon. Now suppose you are using the same process, but you are taking out the carbon dioxide, then it is no more black or gray. Then it becomes blue hydrogen. So what is blue hydrogen? You are using the same process of black hydrogen like from coal, but you are taking care of the carbon. You are taking it out, not releasing in atmosphere. Then this hydrogen is called blue hydrogen. Okay. Of course, the best is green hydrogen, which we want. That is, the process, entire process has no carbon coming out, so you don't have to take care of any carbon. So this is just another definition of how these processes, brown, gray, etc. And you may also have other colors, yellow, pink, etc. having different combinations of this, etc. So here you will learn one term in blue hydrogen. It's called carbon capture storage. That means you have to capture the carbon dioxide or monoxide and store it. So it is carbon capture storage or carbon capture use. That is, the carbon can capture it and use it in another process in some other parallel industry, maybe say Tata Jamshedpur, which is making steel, is using a lot of energy, is using hydrogen, is also producing carbon dioxide or monoxide. But it has another plant which takes in that carbon monoxide or carbon dioxide and produces something else. Okay? So you must, this is a very important term, carbon capture and use, or carbon capture and store that carbon somehow
and it is not released to atmosphere. So then you have got the blue hydrogen. So green hydrogen is the only commercially available hydrogen which can be used today. You have to have storage. So this is another point. Why hydrogen? Hydrogen is a flammable gas. So you have to be very careful how you store hydrogen. Hydrogen can be stored in cylinders. Okay? Hydrogen can be stored in materials. So there are alloys. The most famous among them is lanthanum nickel 5. This research has been going on for 40, 50 years. Okay, how to make hydrogen be absorbed in metal alloys. And a lot of technology has been developed. But it was slowed down in the middle because the government did not put pressure. Because it will cost you some money to make that kind of alloys. But now it has come back again. Because now all governments see that there is no way other than making pure hydrogen. So again there is tremendous interest in making materials which can store hydrogen. So there are alloys, there are also compounds called metal organic framework compounds which can store hydrogen. So those are new, developed in the last 10, 15 years. So you can store hydrogen. The point is hydrogen store is very easy to use. The moment you release it, so you store it under high pressure. The moment you lower the pressure, hydrogen will come out. You can use it. So use of hydrogen is very easy. We can also store energy like in batteries, etc. Right? You can store energy in capacitors, supercapacitors. Right? But they have some additional problems to take care. Hydrogen you can use directly. Problem is safety concerns are there. That's why if you have hydrogen tank in your car, many people are don't feel safe. The world has shown there is safe technology. There are hydrogen cars in the world, shown many years back, and many are now sold in the market. You can buy hydrogen fueled car. You can buy hybrid cars which can run hydrogen electric, hydrogen petrol. So there are other things. So if you use hydrogen as a fuel in your car, then you need hydrogen stations. So there are, in Delhi, there are gas stations, you can fill hydrogen. So only in big cities they have started, but we have only few in Delhi, Gurgaon area, where you can directly fill hydrogen into your car. So it will now grow in big cities, there are more cars with hydrogen, it will grow. It will take some time. So you can use green hydrogen for storage. And of course you can use for plants, etc. What I was telling you about Paris Accord, and every year that review. So recently this review was held in Egypt. India also participated and our foreign minister was there, environment minister was there. And this is called Committee of Parties, COP. This was at COP 27 meeting. The report I am discussing was held just before the meeting. So it was released that this meeting is going to be held, say 10 days later. What has this achieved in the last 1 year? Because it is a review. It is like you are in class 8, when you go to 9, you have a major examination to know what have you learnt in this year. This was like that. This was a review. एक साल में क्या किया, किस country ने क्या किया. So that was released, and I'll show you. So you can see China has the maximum. What is GHG? The greenhouse gas emission. Greenhouse gas are the gases which you don't want, which are producing the greenhouse effect. The greenhouse effect is like going to increase temperature, right? It creates a situation, those gases create a situation that the temperature on Earth will go up. Those are called greenhouse gases. So if you see in 2020, the greenhouse gas of China and then US and India is number 3. But because India has huge population, China has huge population. If you divide by the population, then you see India comes down to some 9th or 10th. So So total production India is number 3, but per capita we are like 9th and 10th. These are all parts of the reports. And so how much China has increased, how much USA has decreased, so all that is reflected, it's all discussed. Who is increasing in greenhouse, who is decreasing in this. So you can say India is plus 3.2, so it is a little higher like that. So these are all things one keeps in mind today. So which are the industries which are producing, they will have more pressure to change their way of operation. Solar power generation, because that is what we need more, solar power, and then convert solar to energy, to hydrogen or some other, solar to electricity through photovoltaics. So, but you need a lot of solar power. So India is producing a lot of solar power. India, China, US, Australia, Brazil, these are the countries we produce a lot of solar power, but then per capita it is very less. We have a huge population. So although it appears we are producing a lot of solar power, but actually per capita it becomes very less. So what is the need? What are countries have been told to do? All this. The electricity at home, industry, transportation, buildings. These are the major areas which take up energy power. So we have to change the way we do things, the way we build buildings, the way our buildings are. So if you go today to a sophisticated building built in Noida or Gurgaon, it's totally different than any building you will see here. There's all kinds of sensors, all kinds of things you have to build according to those laws. But for electric power supply, the government, these are all told to the government, you cannot give subsidy on coal, petrol. You cannot give subsidy. You have to prepare an electric system based on renewables. So how many new plants have you set up based on solar or wind, which is giving electricity? These are all the directions given to governments that you have to do these things. Okay? Expand renewables. For industry, you have to, because steel is a major. What is the most important industry in the world? Steel and cement. They use tremendous amount of energy. So they have told clearly, develop zero emission steel. So it will affect the Tatas or companies producing steel. Who produces Tata, right? So they have to put in plants so that they have to follow zero emission steel. That means while they are making their steel in their blast furnaces and all, not much carbon monoxide, dioxide, if it comes, you have to have a parallel process to capture that carbon monoxide. Next one is cement. You can't make cement today. All these big industries, there will be inspectors checking Ambuja cement or this cement or that cement. How are you making this cement? By what process? And how much carbon dioxide is coming out? So you have to trap that. You know, we did a small project with NTPC. We captured carbon dioxide coming out of their, you see those chimneys? So we put some nanostructured material and we took out the carbon dioxide as carbonates. You can convert carbon dioxide into carbonates. There are some useful carbonates which is used by other industries. So we made sodium carbonate which is used in some other industries, and that is nanocrystalline sodium carbonate. Very expensive. So one project with NTPC we did. So you can do many things you want, and then you have to create this word also you people should know, which is very common. It's called circular economy. That means whatever you are doing, you cannot have any waste which is coming. Anything coming has to be reused somehow. So if carbon dioxide is coming, you have to use it somehow. Some toxic gas is coming, it has to be reused somehow. Or some metal is coming, which is toxic. You cannot put it on the ground just like that. Okay? So you have to create, as far as possible, circular economy. You have to electrify. So I did not, it was there. How will we reach these targets? We still have places, 50% of the population of the world does not have electricity. Do you know this? I think I have a slide, I'll show you. So you imagine how they are cooking. They're all using lakdi or something like the coal. So it will create so much carbon dioxide. Right? People don't understand when you are sitting in a house with all that. We also cooked. I know my grandmother used to use angethi with koela. She did not know what is the harm of all that smoke going into her body, sitting in that kitchen which is closed. Because knowledge in Iraq. Now that we have knowledge, right, that we are telling that these are all very harmful, not only to you, to the entire atmosphere, right? So all that, you have to minimize transportation, expand. Everywhere you see, they are writing, expand electric vehicles. आपके रोड में कितने ट्रक्स हैं आप देखते हैं इलेक्ट्रिकल? Very few in India, right? All the trucks which are carrying petrol have to be electric trucks. Although you are carrying petrol, this is the recommendation of the committee. Your trucks should be electric. Your buses should be electric. Delhi has now some buses, right? But that's the future. All these are recommendations that you shift mode of transport. So increase metro, increase super fast trains, right? Suppose Delhi Ghaziabad is not far, but now we have built a super fast train from Delhi to Meerut. It goes very fast, 160 kilometers per hour. So you have to have very fast moving trains so that people can come from 70 kilometers to office, right? So populate the city and also give them transport which is not dependent on fossil fuels. So it should be electric mobility, subways and this. So now, for example, in Delhi, it is very common to see professors going in metro. I have traveled. I have to go to Delhi University, I can take a metro. I go to airport, I have taken metro and gone to airport. So every Delhi is very well mapped now. But all cities are not today. Even in Hyderabad, Pune, I don't know Pune, Hyderabad, there are few lines, one or two. It's not well connected. Unless it is well connected, people will not go. If I am not able to go from any point to any point, then I will not go to the metro. I will take a car, right? But if I know, if I get into any metro in Delhi, I can go to any corner of Delhi by changing metros, like in Singapore or Kuala Lumpur, or say Paris, or London, right? Imagine London metro, how old it is. Actually, our metros look so shiny. They are all new, Delhi metro. But London metro is, it does all that shaking and all that. It's so old. But imagine when they built it. There are metros running 4 floors, 4 lanes जा रहे हैं, एक के नीचे. Now in Delhi we have 2 lanes, one below the other, but very few cities. But metro building is expensive. You must have people traveling metro. उतना पैसा खर्च करना चाहिए. Metro is 1 kilometer of metro takes how many thousand crores or I don't know. There is a lot of money involved. But that is what is the thing. You have to go from हर आदमी गाड़ी चला रहा है जो कि दिल्ली बॉम्बे में दिखता है उसको बंद करना है. You have to have massive multimodal transport. That means घर से गाड़ी मेट्रो स्टेशन में पार्क करना है and then metro लेके ऑफिस जाना है. The local connectivity you can do with your car. Even that is being provided in many places. They give you buses or based on CNG and all. वहाँ पे भी आपको पेट्रोल नहीं यूज करना है. You have to use CNG, compressed natural gas, right? Things which does not give you carbon dioxide. So all these recommendations, building, minimize, zero emission building होना चाहिए, and all sensors so that you cut down and आपका पूरा corridor में there should be no light unless somebody enters. It should switch on automatically. So you have to put sensors now in any. I believe it must be in all cities. It is there in Delhi. अगर आपको आज होटल बनाना है, you have to put sensors in corridors, in bathrooms, and everywhere, where footfalls determine how much energy is being used. If there is somebody, light will come on. If there is nobody, then the light should not come on. All this is part of the building rules. National Building Code. There is something called national building code. You have to adhere to that. नहीं तो तुम्हारा plan नहीं पास होगा. You see, what I am telling, that 1.5 जितना उन्होंने बोला अगर ये सब करोगे तो भी 1.5 डिग्री राइज होगा 2100. 2 डिग्री अगर नहीं करोगे तो 2 डिग्री राइज होगा, अगर करोगे तो भी 1.5. That means you still have problems. You still some countries will go underwater. That means already हमारे हाथ के बाहर चला गया. That's what it is telling. That more steps for limiting average temperature. What they are saying, there should be no use of coal after 2030. That's the last. Right? Zero carbon power should go to 65 to 90% by 2030 and 100% by 2050. Right? ये होगा, unabated coal needs to fall to zero till 2030. But ये होगा नहीं. How is it possible? अब देखो, अभी 50% के पास kind of irregular electricity. तो 50% को आप इलेक्ट्रिसिटी कहाँ से दोगे? अभी तो प्लान ही नहीं है. 10% के पास है ही नहीं, और 40% के पास इरेगुलर है. समटाइम्स पावर कम्स 2-4 घंटे के लिए. So how will we achieve 65 to 90% by 2030? बहुत मुश्किल है. So we will reach somewhere 1.5 to 2 degrees centigrade rise in temperature. And imagine the earth में कितना ice पानी में कन्वर्ट हो जाएगा. वो सारा ocean levels को बढ़ा देगा. Entire marine statistics जो है वर्ल्ड पूरा चेंज हो जाएगा. This is the energy today. We are around, you see, 36 plus 23, 50, 59 and 2. Around 62% is all fossil fuels. World use कर रहा है, पूरा world, right? India is around 56%, 57%. तो हम world average से थोड़ा कम है, right? So we have to decrease that. What are they saying? That what today we are using, the world is using 63%. It should come to 35% in 8 साल. कोई chance ही नहीं है. The way things are, right? So we have a very tough problem ahead. To all of you youngsters, you will see 2030 for sure. You may also see 2050, and you will see what the earth looks like. इंडस्ट्री को क्या क्या चेंज कर, इंडस्ट्री क्या करता है? इंडस्ट्री देखो कोल यूज करता है 27% और 24% नेचुरल गैस और 26%, 75% फॉसिल फ्यूल यूज करता है इंडस्ट्री, नियरली 75%, राइट? सो मेजर चेंज रिक्वायर्ड. द काइंड ऑफ ट्रक्स आप हमारे रोड पे देखते हो, उनकी हालत देखी है. आर दे एफिशिएंट? नॉट एट ऑल एफिशिएंट. दे आर सो पुअरली मेड, डिजाइन. ज़्यादातर ट्रक्स इधर उधर. In the cities you may see little better trucks because थोड़ा tight है, चलान हो जाएगा, right? So you need major changes in transportation. They use lot of energy, right? Cleaner agriculture. We have very, because our agriculture is very small lands, ना, mechanized नहीं है, तो कोई जैसे मर्जी agriculture करे, काट के जला रहा है, ये कर रहा है. There is no organized agriculture. Unless you have organized agriculture, you can't put these things into place, right? So that's why government of India, we have tremendous amount of money government is now giving if you are working in technology for agriculture. For example, IIT has been asked to develop a department for interventions in agriculture engineering. The IIT does not have it, except IIT Kharagpur. There is no IIT where there is an engineering in agriculture. Because हमारे देश में होता ही नहीं है. हमारे देश में सब छोटे छोटे फार्मर्स होते हैं, वो सब हल चलाते हैं. आपने देखा है 100 acre फार्म इंडिया में कहीं, यूएस में 200 acre फार्म, 300 acre फार्म, all controlled by computers. Everything is given water, nutrients, designed through feedback mechanism. Soil में पानी कितना है, वो assess हो रहा है through sensors. It goes through a central command. That central command hub is basically computers and workstations. that calculates अभी soil में ये कम है, इतना phosphate देना है, इतना यूरिया देना है. It then injects. अगर आप कभी बड़े एयरपोर्ट में जाएंगे, थोड़ा सा आप देख पाएंगे कि all the plants में पानी जो आता है it's through pipelines. अगर आप दिल्ली एयरपोर्ट के बाहर जाएं, नोटिस करें, आपको केयरफुली देखना पड़ेगा, वो पाइपलाइंस दिखती नहीं है, राइट? दे आर ऑल कंट्रोल्ड, नॉट मैनुअली. इट्स नॉट पॉसिबल टू कंट्रोल थ्रू कंप्यूटर. सो कितना पानी देना है, कब देना है, ऑल मेजर एयरपोर्ट्स इन आवर कंट्री ऑल्सो आर डन लाइक दैट. राइट? दैट सिस्टम वाज ब्रॉट इन बाय इजराइल एक्चुअली थ्रू हाइड्रोपोनिक्स एंड ऑल दैट. राइट? बट नाउ ये तो सिर्फ पानी है. But what I am saying in agriculture that आपके पानी के अलावा you need fertilizers. So that's a different ball game. If you go to California, huge tracts of land, it's all automated, right? You will see one machine going, threshing machine, one machine which is huge, इस हॉल से डबल होगा, वो पानी दे रहा है, it rotates और वो चलता भी है. अभी इस पार्ट में है, then it will move to another part of the. So that's mechanized farming. So you can reduce any loss of energy. अगर उसी जगह में हम कोई और टेक्निक यूज करें काटने का, 50 मशीन छोटे छोटे यूज करें, we will have much larger use of fuel, etc. So you have to bring in cleaner agriculture techniques. Okay? Today, according to currently दुनिया जैसे चल रही है, we produce 58 gigatons of carbon dioxide. We will be producing in 2030. अगर हम जो policies बोल रहे हैं maintain करेंगे, तो 52 gigatons मिलेगा. और चाहिए क्या दुनिया को? 40 gigatons. Then we will be at, वो हम अभी भी नहीं कर पाएंगे. We are still at a gap of 12 gigatons positive than what is recommended for 2100. अगर 2 डिग्री राइज से कम करना है, तो आपको ये 12 गीगाटन कैसे कम करेंगे, ये सोचना है. सो दीज आर द थिंग्स द वर्ल्ड लीडर्स आर थिंकिंग. ठीक है? सो क्लीन एनर्जी, ग्रीन एनर्जी में थोड़ा फर्क है. क्लीन एनर्जी, ग्रीन एनर्जी में आप कार्बन डाइऑक्साइड नहीं भेज सकते, राइट? यू हैव टू यूज रिन्यूएबल्स लाइक सोलर, विंड पावर एटसेट्रा टू जनरेट योर एनर्जी. So these are the sources of green energy normally. For geothermal, आपने कभी सोचा ही नहीं होगा. धरती के अंदर बहुत पावर है ना, because we have a molten mass, and sometimes the temperature inside is very high. If you dig, that comes out in some places like geysers. Geysers means hot water fountains, right? So जहाँ पे ये ज़्यादा है, for example Indonesia, Philippines, इस बेल्ट में बहुत ज़्यादा है, वहाँ पे इसलिए volcanic eruptions भी होते हैं. So Finland, Iceland, 70% of its power is geothermal. They are using Earth's energy. So they dig in, reach that place जहाँ पे hot water है. That hot water से वो turbine चलाते हैं. The hot water can pump, and you run a turbine and generate electricity. World's largest geothermal power is produced by Indonesia. Huge, some 1800 kilowatt hour. They have capacity to produce 29,000 kilowatt hour. But there are many countries, including Kenya, many Philippines, as I said. You can generate hydrogen by several means, but you want to produce through photocatalysis, biophotoCatalysis, or electrocatalysis. This will give you green energy. Otherwise, you will get carbon dioxide, and you have to then abstract the carbon dioxide. So some of the best methods to make green is through water splitting. पानी को split करना है through electrolyzers. So India is now going big. India has launched its hydrogen mission, and we are several huge electrolyzers are going to be set up. One near Pune, one near Sonipat, IIT Delhi, and something. Government is going to put up 5 huge electrolyzers to split water by passing. So we can use semiconductors. As I said, when light falls, it creates electrons and holes, and these electrons and holes have to be channelized to create hydrogen and oxygen. We can also use electricity, but ये electricity कहाँ से लाएंगे आप? आपको either hydroelectric use करना है या आपको wind energy use करना है. Yeah. So electrical water splitting is possible. Solar water splitting is possible through semiconductors. It's called solar photocatalytic, right? Photocatalytic. But you can also use with no catalyst, direct solar. That's called solar thermal. That means you need to focus the sun's rays कि पानी ऐसे ही split हो जाएगा. This is done in some countries in Eastern Europe, etc. So water splitting is not new. 1789 it was discovered. This is huge history, but this is scientifically the change. 1972 there is a Nature paper. All of you know who are in science people. Nature is one of the world's leading journals. So this is by a Japanese group. It showed how you can split water using photocatalysis. So hydrogen production using photoelectrochemistry, lot of work you can do. You can design electrodes on which sun shines and holes and electrons are created. Then you can remove this. You have to remove the holes and electrons because otherwise the holes and electrons want to recombine very fast, right? Within say picosecond, right? How to remove them? That's all the chemistry. How to design these electrodes? You can do a lot of things to do that. So I said you can just by sun you can use several methods. Using a catalyst, without using a catalyst, solar thermal, using a material which converts methane in the presence of light. Okay, this has another name. It's called photothermal catalytic process. So here you are adding some hydrocarbon, but you are getting hydrogen. You can also use some biological organisms convert solar into hydrogen. But how to increase the scale ki bhi baat hai. Doing it in the lab, making small amount of hydrogen is something. But doing it large scale, can you have a huge pond, which has all those biomass, then you can produce maybe for few houses near that pond, or for a village in that pond. So that's using biology. So this is something in our lab. So we make such materials. These are semiconductors, and we convert solar into hydrogen. So this is like 6%, and this is another one which has low percentage. The world's record in the lab is 30%, but most of the time that number is not right. It's actually 10-12% because they show it in a way. So the real number, if you ask me, is somewhere between 10-12% efficiency. Okay, how do you separate electrons and holes? These are different designs. For example, this is the semiconductor. You attach carbon nanotubes, or you attach something like graphene oxide. It takes away electrons, and these are for those who are doing little bit research here. They will understand. We are modifying the structure to take out the electrons and holes, separating them. I think my time is over, so I hope the lights on means time is over, right? No? The time is not over? Okay, then this is research level what we do for our PhD students in any IITs or university. What he will study in a photoelectrochemical cell is he will make a cell which is a 3 electrode cell, right? One can be a photocathode. That means it has a material based on a platinum substrate or some glassy carbon substrate. We put a material, a thin film, and you shine light on that, right? If it is an anode, then if we shine light, it's called a photoanode. If it is a cathode, shine light, we call a photocathode. You can have only one or both which produce charges. Then you can have only one. So you can either produce hydrogen, or you can produce both hydrogen and oxygen, and both electrodes. Different combinations are possible. It all depends on how much energy the photon is carrying. and what is the energy gap in the semiconductor catalyst. In the semiconductors, all those who are studying physics and maybe chemistry also, you know there's a band gap and you have to excite an electron from the valence band to the conduction band, then only those electrons are available for charge carrying capacity. So this solar photon, because sun ka radiation bhi is you know, I don't have that scale, okay, I don't have that slide. Solar radiation which comes, suppose I am able to catch all the photons. So out of 100 photons coming from the sun, 4 photons are in the UV region, 43 photons are in the visible region, and remaining kitne reh gaye? 53 photons are in the infrared. The infrared is very long. The entire electromagnetic spectrum have low energy photons, high energy photons. So you have very low energy, the microwave, very high energy photons in the cosmic rays. हम आप जिस photons से देख रहे हैं, that's in the visible range, right? That's why I can see you. If suppose I take out all the photons, visible range from this room, suppose the light coming from all these bulbs, I put filters such that it absorbs all the visible, they dark ho jayega. But you will still have photons. They may be from infrared and UV, but we can't see. Our eyes, right? It's also a biochemical process. The photons fall on our retina, and you know there are something called rods and cones inside the eyes. So there's some chemical reactions. Then it sends a signal, right? There's a protein here, the naam bhul gaya, very chem. He will talk, okay. He'll talk on that. That's interesting, right? So he'll talk to you. Rhodops, what is it? So that will send then a signal to the brain. Imagine, आप सोच भी सकते हो इतना कुछ हो रहा है, आपको कुछ पता ही नहीं, आप पैदा होते हो, बड़े होते हो, मर जाते हो, आप इतने लोगों को देख आपको पता ही नहीं बैक्टीरियल रोडोप्सिन भी कुछ कर रहा था, राइट? इसीलिए पढ़ाई लिखाई जरूरी है, हमको पता है कि क्या हो रहा है, हम क्या कर रहे हैं. That is why you need science to understand and be relevant in society and be relevant in technology. Otherwise आप अनपढ़ गंवार हो जाओगे ना. आपके हाथ में मोबाइल होगा, आपको पता ही नहीं मोबाइल कर क्या रहा है, राइट? मोबाइल सिग्नल कैसे कैच कर रहा है, आप एक नंबर दबाते हो, anyway, what I was going to tell you is that these energies which we are talking, the visible, that has maximum photons in solar radiation, 43%. तो अगर आपका जो भी आप बना रहे हो वो प्रोसेस अगर विजिबल फोटोन से काम करता है, इट विल बी मोर एफिशिएंट, क्योंकि फोटोन्स ज़्यादा है. अगर वो इंफ्रारेड या इससे ऐसे टेल में चला जाता है तो आप काम नहीं कर पाओगे. एक तो इंफ्रारेड की एनर्जी कम है, तो इलेक्ट्रॉन ट्रांसफर नहीं होगा. अल्ट्रावायलेट की एनर्जी ज़्यादा है और 4 ही फोटोन है, 4%. सो यू वांट टू यूज विजिबल रेडिएशन. तो हम केमिस्ट्री लैब में क्या कर रहे हैं, तो लोगों के रिसर्च का थीम क्या प्रोजेक्ट है, ऐसा मटेरियल बनाओ जो विजिबल एक्टिव, बट वो सस्ता भी होना चाहिए, तो आराम से मिलना चाहिए. ज़्यादातर जो आराम से मिलते हैं वो विजिबल एक्टिव नहीं होते हैं. हमारा काम है उसको कैसे विजिबल एक्टिव. सो द वर्ल्ड्स मोस्ट यूज्ड मटेरियल इन एनीथिंग ऑफ सोलर कन्वर्जन इज टाइटेनियम डाइऑक्साइड. टाइटेनियम डाइऑक्साइड पूरी दुनिया में अवेलेबल है और वो बॉडी को हार्म भी नहीं करती. सो इट्स अनदर थिंग यू मस्ट नो. आपको जो भी काम आगे करना है ज़्यादातर सस्टेनेबल होना चाहिए, बायोकम्पैटिबल होना चाहिए. कि आप कोई क्रीम लगा रहे हो, राइट, इट शुड नॉट बी टॉक्सिक, राइट. सो TiO2 creams are available. Zinc oxide is also, but TiO2 is in the UV radiation, उसका बैंड गैप UV में है. तो हम TiO2 UV वाले को हम कैसे विजिबल बनाएंगे, ये आधी दुनिया का रिसर्च है, राइट. हम कर सकते हैं. TiO2 में थोड़ा सा नाइट्रोजन डाल दो, TiO2 minus X NX, ऑक्सीनाइट्रोजन, थोड़ा सा नाइट्रोजन, उसका बैंड गैप चल रहा है, ठीक है. या TiO2 एक लेयर बना, उस पर एक और लेयर डालो, जैसे आयरन ऑक्साइड, which is again biocompatible. Iron oxide will make TiO2 work in the visible region. It acts as a sensitizer. These are called heterostructures. So ये रिसर्च कौन करेगा? ये लाखों बच्चे करेंगे जो लैब्स में जाएंगे. They will figure out which material is good, right? Get better efficiencies. आप इलेक्ट्रोकेमिस्ट्री से भी कर सकते हैं, कोई लाइट की जरूरत नहीं, ठीक है ना? बिजली देना है, वाटर को ऑक्सीजन एंड हाइड्रोजन बनाना है, बट ये इलेक्ट्रिसिटी आपको कहीं से लेनी पड़ेगी. सोलर तो ठीक है फ्री में आ रहा है ना, इलेक्ट्रिसिटी तो आपको यहाँ पे देनी पड़ेगी. तो वो इलेक्ट्रिसिटी कहीं बन रही होगी किसी और सोलर सेल मीडिएटेड प्रोसेस या विंड मीडिएटेड प्रोसेस. अगर आपके पास ऐसा एनर्जी है या हाइड्रो इलेक्ट्रिक प्रोसेस है, देन यू कैन यूज दैट इलेक्ट्रिसिटी. जहाँ पे आप अंधेरे में बैठे हो, बट आप वहाँ पे वाटर स्प्लिट कर सकते हैं और हाइड्रोजन और ऑक्सीजन बना सकते हैं, राइट? पर उसके लिए भी कुछ स्टेप्स हैं. यू नीड सर्टेन एनर्जी क्राइटेरिया टू इवेंट. 1 mole of hydrogen to form, you need 237 kilojoules of energy per mole. Okay, ये standard thermodynamics. डॉक्टर रमकांत बताएंगे शायद, अपने इनका इलेक्ट्रोकेमिस्ट्री का लेक्चर है, राइट? तो ये है इलेक्ट्रोकेमिकल सेल, इलेक्ट्रोकैटलिस्ट. इलेक्ट्रोड पे जैसे मैं पहले कह रहा था, फोटो कैटलिस्ट लाइट आती है, ये इलेक्ट्रोकैटलिस्ट है, इसमें लाइट नहीं आएगी. इसमें यू विल हैव अ बायस, यू विल हैव अ वोल्टेज ड्रॉप अक्रॉस द इलेक्ट्रोड्स. एंड आई थिंक ही विल टेल यू वर्ल्ड का दुनिया का सबसे अच्छा कैटलिस्ट कौन सा है? प्लैटिनम, बट बहुत महंगा है. तो साइंटिस्ट क्या कर रहे हैं? आपको अर्थ अबेंडेंट कैटलिस्ट में आपको ऐसा मटेरियल कम यूज करना है जो महंगा है, मतलब पूरी दुनिया में ही बहुत कम है. मान लो एक ही देश में पाया जाता है, चिली में, तो हम बाकी देश तो वहाँ से मांगेंगे ना, तो हमको खरीदना पड़ेगा. और जो देश बहुत बड़े बड़े हैं, जो चालू देश हैं, उन्होंने पहले ही कब्जा कर रखा है. आधा अफ्रीका, अमेरिका और यूके और फ्रांस बैठा हुआ है, और चाइना ने साउथ अमेरिका कैप्चर कर रखा है. सो इफ यू डोंट नो, रीड these magazines. That's why you must have all round understanding of geopolitics. Science goes with geopolitics, technology. आज हम कभी करते हैं ना कि हम कतार के साथ इंडिया एग्रीमेंट साइन कर रहे हैं, या हम कल बोलीविया के साथ साइन कर रहे हैं, क्यों कर रहे हैं? फिर हम इंडो बोलीवियन हम साइंटिस्ट भेज रहे हैं केमिस्ट्री के लिए. जरूरी नहीं है इंटरेस्ट केमिस्ट्री हो, इंटरेस्ट कहीं और किसी चीज़ में हो, बट 2 देशों को पास लाना है ना, कुछ करना पड़ेगा. That's why the government of India has think tanks which plan strategy. What is the strategy? Now IIT Delhi is opening campus in Abu Dhabi. Abu Dhabi में क्या मिल रहा है आपको? Now why is it so important? You have tremendous interest in Abu Dhabi. So like that, we make friends where we have India will be supported in the long range. So we'll make friends in those countries, right? Because उनको चाहिए कुछ नाम, IIT का नाम, उनको एक इंस्टीट्यूट वहाँ खोलना है. We want something which if you read newspapers you may get an idea, but I leave it for you to understand what is available in Abu Dhabi. Like that there are many countries which are important. बायोमास से भी हम बना सकते हैं, बट बायोमास से क्या होता है? कहीं कार्बन बनेगा, आपको एक रिफॉर्मर के थ्रू पास करना पड़ेगा, तो कार्बन को निकालना है. many process are there बायोमास से. तो आप देखिए हर जगह हाइड्रोजन के साथ कुछ कार्बन निकल रहा है. जहाँ कार्बन नहीं निकल रहा है, जैसे इसमें, सो आई विल यूज दैट प्रोसेस इज बेटर, फोटोबायोलॉजी. जहाँ बाकी सब में कार्बन या कार्बन डाइऑक्साइड निकल रहा है, सो मैंने बायोमास से स्टार्ट किया है, बट इन ऑल माई प्रोजेक्ट्स दिस कवर. विंड एनर्जी से I can convert wind energy by using converters to be used for different application. For homes के लिए you need AC power. आपको हाइड्रोजन निकालना है तो इलेक्ट्रोलाइजर के थ्रू ले जाना पड़ेगा. So it depends on what you can integrate your wind energy with our national grid, and you can use it for different things. Geothermal, I told you, Indonesia, Iceland, they are maximum geothermal. Same geothermal से आप finally green hydrogen निकाल सकते हैं. So अभी भी दुनिया steam reforming पे ही ज़्यादा चल रहा है. तो आप commercial जितना भी बना रहे हैं, which is grey or black hydrogen. So hydrogen steam reforming. As the oldest technology, we have to slowly decrease that and use electrolysis, photolysis, these kind of programs. So these are the electrolysis pathways I have already discussed. अब ये सारे techniques. Ultimately, हिंदुस्तान में ऐसे electrolyzers हर शहर में खड़े करने पड़ेंगे, large size. So right now there is a 20,000 crore given for hydrogen in India to set up this kind of electrolyzers. These are again non-photovoltaic means जिसमें semiconductor chips use नहीं हो रहे, not non-photovoltaics, जिसमें कि photocatalysis use हो रहा है, या photoelectrochemical use हो रहा है, या photothermal use हो रहा है. Right? This is using bio. I will not go deep, but this is basically, as I said, like chlorophyll works can absorb solar energy. Now people have generated in the lab other such systems which can trap solar energy. But इसकी quantity कितनी होगी? That is the problem. तो आपको large scale में bio करना है, it's not easy. It's a challenge. So all these are possible. I'm going to conclude. So fermentation से भी आप hydrogen use कर सकते हैं. Biomass pyrolysis से भी hydrogen निकाल सकते हैं. Solar, this is what I said, Eastern Europe and all. You have to take direct sunlight और mirrors लगाने पड़ेंगे ताकि आपको focus करके आपको tremendous temperature rise करना पड़ेगा कि water अपने आप breaks down into hydrogen oxide. No catalyst required. You need large mirrors to focus the solar radiation. So this is about storage. So I was telling you, बनाना एक बात है, उसको store के रखना भी तो है, को गाड़ी का tank में रखना है. So you can store in cylinders, you can store in materials, and what are the materials? As I said, hydrides in alloys or in metal organic frameworks like that, and you can see the amount of hydrogen, 70 gram hydrogen per liter in this, whereas पानी में कितना होता है 111 ग्राम 1 लीटर पानी में hydrogen if you can dissipate. So it's not bad, 71 gram stored in metal organic framework. तो आपको metal organic framework सस्ता वाला बनाना है. अगर आपको 500 किलोग्राम खरीदना है, it cannot be expensive. It has to be based on a metal which is very cheap, like iron, zinc, etc. So always when you do now chemistry or science or technology, आपको industrialist की तरह सोचना है, right? क्योंकि आपको पैसे लगाने हैं, आपको एक plant खड़ा करना है, Reliance plant खड़ा करना है. Reliance is putting up hydrogen plant, right? So you have to know which material to use. Metal organic framework 1000 तरीके के हमने लैब में बना सकते हैं. उसमें से कौन सा आपको चूज करना है, जो कि अगर मैं 1000 kg खरीदूँ तो भी मेरे को सस्ता पड़ेगा. It has to be something. आपको periodic table पता होना चाहिए. आपको पता होना चाहिए कौन से ऑक्साइड दुनिया में सबसे ज़्यादा बनते हैं. एल्यूमिना, सिलिका, right? Iron oxide, zinc oxide, titanium oxide. Not something like thulium oxide. किसने सुना है नाम? It's in the rare earths, F block element. But F block element में एक बहुत element है, common है, इंडिया में मिलता है, which is thorium, lanthanum भी common है, लेकिन neodymium. So neodymium is again a very important metal in the world. Okay. So दुनिया कैसे दिखने वाली है आगे? हाइड्रोजन से हम गाड़ी भी चलाएंगे, right? Fuel cell. What is a fuel cell? You pass hydrogen and oxygen to generate electricity. हर घर में छोटा fuel cell अगर हो तो मेरे पास हाइड्रोजन है और ऑक्सीजन मैं एटमॉस्फेयर से कैप्चर कर सकता हूँ, कोई प्लांट में लगा लेता हूँ, आजकल मार्केट में मिल जाएंगे. You can trap oxygen from the air. You need some membranes to purify the nitrogen and all that, and you can get pure oxygen, and you combine, you can get electricity. So you can have fuel cells. Fuel cell large amount में कनाडा ऑस्ट्रेलिया में बहुत सालों से चलती है. घरों में electricity comes from fuel cell technology. But we can also directly use these for fuel cell based cars. So we are using hydrogen. As I said, in Delhi also there are now 2 gas stations where you can directly put hydrogen in your car. So this plot says 2030 में green hydrogen will become comparable to आज हम जो price दे रहे हैं बाकी electricity के लिए, 2030 में with the way governments are going इसकी price कम होती जाएगी, right? So we will meet 2030. So अभी जैसे grey hydrogen अभी $1.8 $2 per kg है, right? ये भी $1.82 के kg आ जाती है. These are trucks, hydrogen trucks. मैं कह रहा था सारी गाड़ियाँ electric, ये तो electric नहीं, hydrogen based है. So they are running on hydrogen. So ये दुनिया में बहुत जगह है, यूरोप में बहुत दिखते हैं. So these are all, this is made by Hyundai. So these are all the entire energy scenario: oil, natural gas, biomass, coal, geo, hydro, tidal, wind energy, solar, nuclear, all of them. How you integrate into the hydrogen energy. So from all these you get grey hydrogen, brown hydrogen, yellow hydrogen, blue hydrogen, green hydrogen, and how you can use it. I stop here. I think I've spoken enough. What? I think I overshot my time. Yes, it keep going, right? Huh? I was asking what is the time. But I asked, is it? I thought I was going over it. Good question. Keep going.
Any queries, please, from the audience? From teacher side? Thank you.
Thank you, sir, for your informative lecture loaded with knowledge. I now request Dean, School of Liberal Arts and Sciences, Professor Jitendra Beenwal, to felicitate our speaker, Professor A.K. Ganguly, sir, with a shawl and memento.
Thank you, sir. I now invite Dr. Soban Sen for his talk on utility of fluorescence spectroscopy and microscopy in chemistry and biology, a primer.
No, I have everything. Yeah. You just can't disconnect. Thank you. any changeover? Yes. Yep. But how to Yes, we are here. Thank you. All right, so I'll now switch the gear a bit. And what we are going to do now is that whatever Professor Ganguly was talking about, we will try to get into those molecular systems and try to understand that how nature sustains itself, okay, and how we can actually try to understand nature and to do something. What already Professor Ganguly already talked about, that how to follow nature and try to do something which is sustainable for us to survive the humankind on Earth. Well, I'll get into some molecular details also. We'll talk about this fluorescence spectroscopy and microscopy. So the microscopy part anyway I'll talk about in the next lecture in the afternoon. So we'll try to involve or try to give some idea of how this fluorescence actually works and how we can understand things. Now I hope that everybody heard this term fluorescence. Anybody? Everybody heard that term or no? Not at all, huh? Well, it's there, here. You see these tube lights here? These tube lights are the fluorescent tube lights, Although nowadays we are trying to change those things with the LED lights, the bulbs, because these are not really good for the environment. Why so? Anybody knows? Why so? Because these tube lights have mercury in it. You need mercury, and once you dispose them off, that mercury goes into the nature, and that we do not want to have, and that's the reason. Now we are trying to replace everything with the LED lights. Now these are the fluorescent lamps. We have seen many fluorescent lamps. Okay, have you ever used? I'm sure everybody has used highlighters, fluorescent highlighters, fluorescent molecules. Okay, have you seen? Okay, night time when you are going through the road, somebody is wearing a particular jacket having a fluorescent, so that nobody goes and hits that particular person if the person is walking on the road. So those are the things. Fluorescence is everywhere, and we will look into those fluorescence anyway. But before that, I'll try to give you some of the general things first, okay, which Professor Ganguly was talking about. Well, the most important is interaction of light with matter, and that how it sustains everything in ourselves in every way. And then we'll talk about a little bit fluorescence. We'll try to do some little bit small experiment over there to show the fluorescence and how the molecules can behave in different manner, and then some fluorescent molecular properties. And in the next talk, probably I'll go a little bit ahead in the more research level and try to show you what you can do with the fluorescence in a much higher level and so on. All right, so when you're trying to observe this wonder world with this fluorescence spectroscopy and microscopy, you have to first understand what do you mean by spectroscopy. Well, if you actually separate this word out, it's this Latin and Greek word coming together. It's all about thinking about viewing something or seeing something. That's the process. And if you really look also very closely this word, it's something like you can think about like a specter plus scopy. Spectre, what is spectre? Ghost. Ghost. So in a sense, we can actually do this spectroscopy with a kind of a ghost scoping. Meaning you will not be able to see something directly. Rather, you can actually look at into a system which is giving you some indirect information. And one such thing, I'm sure that probably everybody heard about Bohr model. If you're doing some chemistry or physics, something like this is what it tells you, that the electron goes up somewhere and then it comes back to the lower level, it gives you the light out. Okay, and that's your all the series, Palmer series, Lyman series, Paschen series, all those things like that. Now this is your spectroscopy. That means you now know this about the things, when you explain. But what you observe is actually this, lines like this. Now this is spectroscopy. That means you are not being able to observe the process there, but you are trying to look at something and then trying to explain what is happening in the system. Okay. What about microscopy? Well, spectroscopy, yes, we'll talk about a lot of fluorescence spectroscopy in this talk and next one. And let's see what we can do. When you talk about the microscopy, yes, micro and the scopy, that means you're again trying to go, very minute, distances or small positions in space and trying to see things. And that is very, very important, had happened what we spent for the last 3 years based on this. That we know how the COVID-19 virus looked like. And you can see this particular paper, okay, 2020. This is the group actually first observed this particular virus under the electron microscope. I'll come to that point later on time when we talk about the microscope in the second year. So you can see this is the sizes of the order of 100 nanometer. And through this, we can now know what is there, some nuclear RNA part and the spike proteins. Everybody knows about the spike protein nowadays, I hope. Everybody heard about that, spike protein? I hope that, she's going to talk about some of the protein structure or something, not the spike protein probably. And with the fluorescence, we can do a lot of things. We can actually see directly the cell divisions and so on and so forth by utilizing fluorescence. So you are actually observing all this, cell division. So this blue color is the nucleus, and these actin filaments, they are getting separated. The mother cells are becoming daughter cells and so on and so forth. You can actually observe. This is the real, live cell imaging that is happening under the microscope. You can do that. That's the microscope. Well, you can actually look at all this. Yes, this is what? This is actually from our lab. This is a kind of a, E. coli bacteria. You can actually see that under the microscope, E. coli bacteria. And if you actually treat this bacteria with the antibiotics, okay? You take antibiotics if you have some problem, stomach, a problem, you have antibiotic, cephalosporin, something. It becomes like that. That's the way it actually gets broken and it gets damaged. Okay, so you can see these things under the microscope with the fluorescence and many other processes. All right, so what is spectroscopy? That's one of the first thing. It's all about the interaction of radiation with matter, or light with the matter. That's what Professor Ganguly was talking about. And the light is nothing but your, either it's a wave-like or a particle-like. Wherever I want to utilize either with a wave or a particle, I utilize it, whatever the way. Now this is light, and when you talk about the light, this is one of the most important region. Okay, what Professor Ganguly also mentioned very, very nicely, that you need to have this particular small region of the entire electromagnetic radiation which actually sustain life on the earth. And I'm coming to the next slide anyway. Okay, and the light, you can explain with some mathematical expressions what Maxwell's have given, and this is what is the most important question. Now you ask that why it is so important. I'll give you only 2 examples here with some very details of it, which already Professor Ganguly was talking about, and then we can get into more details. Well, matter, everything is matter, starting from your leaf, molecules, atoms, everything. We'll get into up to this molecule level. We'll not go into more to the atoms and something like this. But yeah, these are the matter. These matters will interact with the radiation which is falling from everywhere. Let's say main source is sun, and then we can do a lot of things. And one of the most important sustainable thing is the photosynthesis. What Professor Ganguly was already mentioning, that how actually it works. Well, probably we can try to look at. I don't know whether you people have looked into this process or not. Okay, I don't know whether it will. Yes. So this is available in YouTube, but the most important factor is this: that what it happens in this, that you have the ingredients, these 3, and you are actually making the output as a glucose. That's your food. That's you need. And as a byproduct, you are getting the oxygen. Okay. Now, how it happens? What Professor Ganguly was already talking about, that these photons of light falling onto my leaf, and if you get into deep inside the leaf, what you have, we all know, we are reading from our school days, this dark phase, bright phase of the processes, and this is your chloroplast. And if you get into the chloroplast, what happens? There are these hycoloids and other parts of the system, which is typically, you can go over here, and that thylakoids is there, and this is your membrane of your cell, and this membrane will have some important molecule, which is called the chlorophyll molecule. Okay? And if you expand now this one, so it will get into the expansion mode, and we'll try to see how this process really happens. So this is your stroma, and this is the thylakoid space, and this is your photosystem 2, and this is your photosystem 1, which actually absorbs the photon from coming from the sun. And what happens? This one, these photons are getting absorbed, and they are getting channelized through a energy channel inside this, B6 complex in the light harvesting system in our plant, and these energy is getting channelized into a particular center, and when some electron is coming from the dissociation of the water molecule, these electrons are getting energized. Only when this electron gets energized, it goes to the next step, and it starts the process of the photosynthesis. Now, the most important fact over here is that you need the light photon to come. Otherwise, even if you are splitting the water molecule into the hydrogen and oxygen or electron here, this electron will not be energized. And once it is not getting energized, you will not be able to start the process. So the first process is nothing but the absorption of light. Once the sun dies, by the way, this is the way it happens. The water gets split up, one oxygen comes over here, 2 protons are over here, 2 electrons over here, another water molecule comes over there, it splits and it joins, give you the byproduct, which is your oxygen molecule. So the process is been started by this absorption of photon, and then only it can start doing the actual synthesis of your food, that is your glucose. Okay. Now this already know, and you can actually get this one also in YouTube. That's pretty a nice video. It really tells you how really what happens in the system. Now you can ask this question, okay, why the color of the leaf is green? Anybody? And the answer is here in this slide. Why the color of leaf is green? Bolo? Why? Why? You have to talk in terms of spectroscopy. We're looking into spectroscopy, lights and everything like that. Okay. Anybody? Anything? Any better answer? Huh? Okay. Anybody can see this one? Okay. What is this? This is your absorption spectrum, or spectra, I would say, of the 2 chlorophyll and chlorophyll B. What you can see, when the sunlight falling onto your leaf, the chlorophyll and chlorophyll B is absorbing my blue region and the red region, but the green region. So what is happening? White light, blue and red is getting absorbed. What is getting reflected? Green. That's it. Who is absorbing? West chlorophyll. That's what you are trying to say. This is your chlorophyll real absorption spectrum, and that is getting absorbed, is giving you back the green color. That's the color of light, leaf is green in general. All right. Another very, very important, again, Professor Ganguly was talking about. Okay, vision process. Right now we are doing it. How? Again, spectroscopy. How? Okay, this is what it happens. All right, this is what you have in your eye, rod cell. We know rod cells and cone cells. Rod cells are responsible for low light vision, and cone cells are for the color visions. Okay, so the rod cell, what is rod cell? Looks like this. If you actually get some part of the rod cell, it looks like this. So you have, if you expand this region of the rod cell, you have this membrane, the cell membrane, within which these kind of proteins are embedded, which is called the rhodopsin molecule. All right, if I can expand this one, let's try to see whether it's expanding something or not. Yes, probably it will do. So it is not projecting the whole, yeah, that's the problem. Okay. Okay, I really cannot see you this because it is not projecting this particular one. Okay, so what happens, let me just tell you, if we expand this particular rhodopsin molecule, then inside the rhodopsin molecule is a barrel-like structure, okay? The barrel-like structure. Inside it, you have a small molecular part, which is a part of the protein, which is called the 11-cis retinal. And how does it look like? This is the structure of 11-cis retinal, okay? This is the structure. So this is the part which is connected with the protein, and when the light falls onto our eye, what happens? It actually goes to the excited state, meaning it absorbs the light, it goes to the excited state, something like this, okay? You have the cis conformation of this molecule. It's only a small part of the entire big protein molecule. It takes the energy, goes from the ground state to the excited state. But you can see this, when it goes to the excited state, your bond order, this 11 position carbon-carbon double bond, gets lower. That means becoming nearly like a single bond like order, and it can rotate very easily. Once it rotates, it gets a all trans conformation, and because now the, earlier it was like this, now it has become like that. Now, to accommodate this configuration of the molecular part inside the barrel structure of the protein molecule, the protein has to expand. In fact, I had that, here. Maybe I can show you later on in my, anybody's interested later on time. Once it expands, it creates an electrical signal. It goes through this G protein coupled pathway to your brain, and you can start seeing. Again, let's forget about all these complicated biological parts. But again, the process started this particular interaction of radiation with the matter. That means H nu is getting absorbed by this molecule, go to the excited state. Only when it goes to the excited state, you can see it can now easily go into and come back to the ground state over here into this all trans conformation. To go from here to here, you have to cross a big barrier, and you have to give a lot of energy to actually get into the system. That can be easily be done by simply absorbing light. That is the way we are observing right now on the screen. It's happening right now in our eye. So these are two important processes which has been sustained by these principles of spectroscopy or interaction of radiation with the matter. All right? So we come to this point that, okay, we know about this molecular spectroscopy, how they can actually control different processes for which we are getting sustained in our life. Then we can get into the fluorescence spectroscopy, and this is kind of a you can say the introduction also to my next talk, which will be a little bit in the higher level, but we'll try to see what fluorescence is all about and how we can do some kind of a simple observation, and what are the properties of different molecules which can give you different things with which you can do many other things. Okay, and I'll try to give some examples of something. All right, when you talk about this fluorescence spectroscopy, has anybody heard this name earlier? Jablonski diagram? Yes, sir. Okay, there are some yes, sirs. Anybody? Jablonski diagram? Yes, sir. Okay, some people. Okay, whoever doesn't know, yeah, here it is. Okay, so what happens, these molecules typically stay in the ground electronic state, and which is defined as S0. It is the electronic state, okay, because you are talking about all the electron clouds, how they are moving from one part to another part. Obviously, electronic states also will have all these vibrational states. That's their fine structure. If you actually go deeper inside the vibrational states, you also have the rotational states, which you can utilize three different spectroscopic, or I would say the electromagnetic radiations to probe, like microwave radiation. You use microwave oven. What you utilize? You actually utilize the rotational levels of my molecules, okay, to rotate the water molecules inside your food particle to heat up your food. You can actually use vibrational spectroscopy, typically the IR, okay. You heat up with frying something in the oil, you're putting at heat, okay. That's one. And also the electronic spectroscopy, I have already given you two very important examples. When the molecule is going from the ground electronic state to the higher excited electronic state and doing a lot of these processes. The most two important processes, that is your photosynthesis and right now like your vision through photoisomerization. Okay, so what happens? You have these molecules. If you are not really putting energy into the system, if there is no interaction of radiation with the matter, the molecules will stay forever in this ground state. Once you shine light, they will go to the excited state depending on whatever the color of the light you have given. If the color of the light is such that the energy gap is looking into S0 to S2, that gap, it will go to the S2 state, and this process, as Professor Ganguly was talking about, this process really takes only around 1 femtosecond. Okay, so this is your femtosecond time that it will take, and immediately once you shine the light, okay, it's there. That is exactly what happens right now. That light is falling onto my eye or your eye. Within femtosecond, the 11-cis retinal going into the excited state, and only after some picosecond times they are coming back to the ground state in the all-trans conformation. So these time scales are very, very important. Now look at this one. Femtosecond is 10 to the minus 15. Picosecond is minus 12. 1,000 times slower. Okay? The process of coming back to the ground state is typically 1,000 times lower, even much larger. If you're talking about the fluorescence, is even more. We'll talk about that. Okay? So this goes to the excited state immediately after the excitation, and they will not stay forever in the ground excited state. They will first come back to the lowest excited state through this process called the internal conversion. Okay? That typically takes around a picosecond or so, something like time, and from there, when they come back to the ground state, can give you some light, and that light is called the fluorescence. However, all these molecules around us, many of the molecules, whatever we are composed of, they are actually absorbing light. They are going to the excited state, but they are not coming back to the ground state by always fluorescing. Otherwise, all of us will be fluorescing all the time. Light is coming out of our body. That's not happening. Why? Because most of the molecules, okay, it can go to the excited state over here, and again it can come back giving you the fluorescence, but it can actually come back many times just by releasing heat as my internal conversion. That actually happens for most of the molecules. So you have to make molecules which are fluorescent. Not every molecule is fluorescent. That's the reason. Your highlighter pen having some particular molecule, that's why it is giving you some fluorescent highlighting. Okay? Or that jacket that worker is wearing on the roadside, that has a material. So not every material is fluorescent. So we'll talk about some of the structures of the molecules and how they can become fluorescent. Okay, so this really the fluorescence process. Well, the molecule can sometimes also go to the triplet state through some kind of a process called an intersystem crossing. Some conditions, not all molecules can show this kind of thing. And once it goes to the triplet state, from there it can come back again to the ground state to give you another light, which is called the phosphorescence, and actually takes much longer time. That is in typically microsecond time, sometimes even getting to the millisecond time scales, because these are not allowed under spin selection rule. Let's not get into all the big details into this one, but this is what happens when you excite any molecule to the excited state. This is the way the molecule can come back to the ground state. Okay, so I think this point is clear, and this is called your Jablonski diagram, which can tell you how the molecule can transit from different states, among different states, what is the time scale that they can actually do these processes in the molecule. So now I at least have some idea of what are the time scales. You can see I have written down this fluorescence time scale, typically how long the molecule will stay in the excited state, around 1 nanosecond. It depends on different molecules, but typically it happens that means it will stay in this excited state around 1 nanosecond or something around that before they again jump back to the ground state. Okay, that's we call it the fluorescence lifetime and so on and so forth. Okay, we can measure it experimentally and so on. Okay, so this is what is all about the fluorescence, from where it actually originates. And this is what you can actually utilize your fluorescence spectrometer, where you can see this is a very important molecule, and I'll again come back to this particular molecule. This is the molecule. This molecule can show an absorption spectrum like this, and the emission or the fluorescence spectrum like that. The most important factor to note here, that if you are taking any this kind of molecule and trying to measure the fluorescence and absorption spectrum, you can see there is always a gap between the absorption and fluorescence, and this is called the Stokes shift. Because what happens, you can go back to this one, you can see even if you are exciting somewhere over here, first they will come back to the lowest vibrational level, and from there it will come back to the ground state. So it is losing out some amount of energy, then only it can give you the fluorescence, which is giving you a kind of a red shift, okay, in the higher wavelength side, that means lower energy. Okay? So that is what we have looked into like this. Again, this is a very interesting molecule. It can also show very nicely the absorption and emission. Another very important thing to note over here, they are almost like mirror image. Okay, and that happens. Once the molecular structure is very stable, you probably can actually have this kind of a condition already maintains, that how the way that it gets absorbed, the same way it can come back to the ground state to give you the emission or the fluorescence. Okay, so this kind of a this mirror image rule is always been given. Not every molecule shows, because there can be different charge transfer state or something like this, but at least these two molecules can nicely show this kind of a mirror image symmetry between your absorption and fluorescence. All right. Now this is where we come in, that not every molecule is fluorescent. You have to make the molecule fluorescent. Okay? And I think this molecule everybody has used in your school days. हाँ? किसके लिए यूज किया था? Acid base indicator. Huh? So what happens, if I change my pH, this hydrogen will go out, this will connect with this particular portion, sometimes these hydrogens can go out, and so on and so forth, and it will go from orange to pink through no color somewhere. The no color is somewhere where actually this one actually goes out and this oxygen gets connected with this one. So water molecule will come and then it will take out, OH will come, they will take out, and then it will fix up, and that will be kind of a no color. So if you are taking this molecule in simple water, which is typically around 6.87 pH, neutral pH, you put in there, what do you see? There is no color. Only when in the low pH or high pH, either orange or the pink. Okay, that too also, those colors are not fluorescent. Those are just like your why the color of leaf is green, kind of. Okay, so these are complementary colors that we are looking into. Now what happens is this. So I have this here in video. So again, you look at this particular one. This molecule and this molecule is very similar. This molecule I just shown in the last slide is having some kind of absorption fluorescence. So once you have a molecule which is just connected over here, these two phenyl rings are getting connected over here, it suddenly gets heavily fluorescent. And you can see this one very nicely in this particular video. So you can see this is your phenolphthalein in water, this is your fluorescein in water. Okay, and now you are shining light into this one. What do you see? There is almost no color, okay, no color at all, but this is your highly fluorescent. The structure is like you have only one oxygen coming together and it is fixing your phenyl rings. And it is blocking the rotation of those phenyl rings. Once you block the rotation, you suddenly allow the molecule to come back to the ground state with the fluorescence pathway. Because I have shown you two pathways to come from the S1 to S0. One is IC, internal conversion, one is fluorescence pathway. So what I'm doing, I'm just controlling the molecular structure to go from one pathway to another pathway. Okay, so that is what really happens. And remember, this is the molecule which actually we use it in the green, yellow marker, highlighter. This is the typical molecule we use over there. Okay, and you have seen the color, this very nice green color kind of thing. Okay, so this is what is interesting. Yeah, I'm doing it good in time, so I'll probably finish it in 40-45 minutes to make up the time. So any question here? It's all understandable here, all how the molecular structure and fluorescence can give you, and these molecules have been utilized in everyday life. Okay. All right. So next, we can talk about one of the very important molecule in terms of your bioluminescence. What you're observing over here, what are these? Huh? Jellyfish, jellyfish. You put an aquarium, jellyfish, and you shine UV light, typically 400 nanometer light. But you see some kind of a bluish, greenish color is coming out of this particular one, which is because of this protein called, acurin protein. So acurin protein is actually gives you the bioluminescence. Okay. One version of that protein is now being utilized as green fluorescent protein, for which these three people was given Nobel Prize in 2008. What they have done, they have extracted these proteins from jellyfish. The first person, Shimamura, and these two persons actually they engineered to improve the fluorescence enhancement of these particular molecules, protein molecules. Now again, coming back to the chemistry, well, we're not doing biology here, so this is your protein. But then the entire protein is not responsible for your fluorescence. It has to be some chromophore, small part, like your fluorescent molecule. Well, the part is here. This part is here. And you can see this molecule, only this part, having the absorption spectrum something like this, okay? It's absorbing something around, 400 nanometer when it is in OH configuration. Once you excite the molecule to the excited state, what happens? The lability or the basicity or pKa, whatever you say, of this OH bond changes such that now the O can go out very easily, and in which a water molecule comes and do this process very, very nicely. Okay? So in this, beta barrel, you also have a water molecule coming close to each other, and that can give rise to some kind of a protonated and deprotonated configuration. Only when it is deprotonated, which is O minus, it will give you this green color or the bluish green color of fluorescence coming out of this molecule. Again, that molecule, the chromophore, is the most important to give you this fluorescence out of this. Okay? Again, this particular process really happens in a very, very fast time scales, typically in picoseconds, 2 to 3 picosecond time scales. We can also measure nowadays experimentally. With the ultra-fast fluorescence spectroscopy, we can measure the time scales, how much it takes time to release this proton to become a tautomar. Okay? You can probably look at this particular paper, long back in a paper, which really measure those things. And later on, many, many people have done it with the many, many different forms of this particular molecule. Why this molecule is so important? Because this has changed the entire biology world. How do we see things under the microscope? Because it's light up. So with the fluorescence microscopy, which I'll talk about in the next talk, where you can see things under the microscope directly, the way that I was showing you that cell division. How you're looking at cell division? Well, that is fluorophores. Blue color, which is fluorophore, and attaching into the nucleus part, which is typically the molecule called Dept molecule. It goes and binds to the DNA inside the nucleus, and the other part is attached with some either green fluorescent protein or some other tagged molecule, which is green color, which is getting tagged with the actin filaments. That's the way we can see and observe in the real time how things are happening. Okay, and that's the beautiful part of it. Once the light is up, once the light is on, I will be able to see everything. That's the concept in spectroscopy, that you shine the light is coming out from a system, you'll be able to observe it. So this is the process. Yeah, this is the process what happens. So this is the part of the protein, this is the chromophore. Its first circulation happens, then dehydration, then again oxygen comes in, and it transfers into the two different configurations. One is protonated, one is deprotonated. And the deprotonated one is your fluorescent. It only happens in the excited state through this excited state proton transfer process. Because that OH is not very happy to give its proton out in the ground state. When it shines in the excited state with the 400 nanometer light, it then releases that proton, and then it comes to that another state, which is tautomar state. And when that one comes back to the ground state, give you the fluorescence. Okay? I hope this is new to everybody, or somebody were new about these things earlier. No? Okay, good, good. So now at least few things we know now, new things. about how the nature works. This is nature, this is natural. And all the other people actually tried to take those things, molecules from the nature and improve them. And the second two, other than Shimamura, the other two, Tijian and other person who had actually engineered these proteins is called the enhanced green fluorescent proteins, EGF we call it nowadays. Okay? Okay, fine. All right, now this is the experiment that I'm going to show you here, that now I'm trying to see that, okay, can I use this fluorescence to understand the environment? What do you mean by environment? Well, some solvents, some solvent environment. Whenever you talk about the solvent environment, the most important fact comes up. Well, the solvent is whether it's polar or non-polar, or a less polar, or a high polar, low polar. What is the most commonly used solvent, the highest polar solvent? Water. Water is the highest polar solvent, high dielectric constant. And we also use a lot of other solvents like ethanol, methanol, then THF, dioxane, ether, many, hexane, all nonpolar solvents. All these solvents are there. So question is that, can we use even this fluorescence to measure that polarity of solvent in some complex environment? Oh yeah, I know what is the environment polarity of my water. I know the dielectric constant, I know the refractive index, everything, the polarity, everything I know. But I do not know, well, if the water stays somewhere inside my cell or near the membrane of my cell, what is the polarity over there? Is it the same like water? Bulk water? Well, maybe, may not be. Can we look into those things? Well, let me first do these things and then. So what happens? You have the molecule somehow in the ground state. You shine the light, some molecules will go to the excited state. In the excited state, because of your solute-solvent interaction, okay, there is this solvation process happens in the excited state. It actually gets solvated to a little bit less energy state. This is solvated state, we call it. From this solvated state, this process actually takes something around picosecond to nanosecond time scale based on wherever you are actually observing. In fact, our main research field actually gets into very much into measuring these kind of time scales with the ultra fast fluorescence spectroscopy, but let's not get into there right now. So what happens? This is solute solvent interacted solvated state of my molecule, of the fluorescent molecule. Now when they come back to the ground state, it gives you the fluorescence. If you measure the fluorescence, it looks like this. Now you take the same molecule and put it into some another environment which is more polar or less polar. If I do a more polar, the solute-solvent interaction will be even more and it will be stabilized even more. And then from there, when they come back to the ground state, it can show you the fluorescence which is red-shifted if the molecule is positive solvatochromic. Okay? So this is what it should look like. A same molecule you are putting in different environment should show you different colors. Can you do that experiment? Let's do it. Okay? So what I have the molecule here, this one. Okay? 4-amino halimide, which is having a high dipole moment in the ground state also. And I'll be trying to utilize few of these solvents and try to see if the same molecule is getting dissolved in different solvents of different polarity. Okay? Let's say water, I have something like, I think, water, butanol, and ether, I think. Yeah. So these are the things you can see. The highest polar solvent is this one, 78, dielectric constant, then it butanol like 17 and something like this. I also have a video, but let's not get into the video because I have the materials now here. So let us see. So what I will do, this particular molecule can be excited around 400 nanometer light, just like your GFP molecule or something like this. Okay, so let me first put on my laser. All right, so this is your laser, which is 400 nanometer. It's almost like similar laser, like this is my red laser. Now this is my, your ear laser, blue laser. Okay, if I can have something. Yeah, can you see this one? Okay, so that's my, blue laser, 400 nanometer light. Now I'm trying to put on some same molecule. Already I cannot make the samples over here, so I made the samples and I brought it. Okay, this is your, let me see, in water, I think. Okay. Okay, I need a small something to, some book or something if you have, because I have to raise it a bit. Okay, okay, let's let everyone. It's fine. What do you see here? Color? Something like yellowish. Anybody can see the color from there? Okay. It's okay. Yes. Which one? No, but then it will be too difficult. I'll put up all the, yeah, that's okay. I'll put up all, step by step, yeah. Don't worry. Yeah. So this is your molecule in a high dielectric constant or the high polar environment. Okay, water. Now, this is your intermediate polarity, which is your butanol. Same molecule. Color is different. Now, the same molecule is even less polar environment. Okay. Now, this is what is the fluorescent marker can tell you and show you that if you put this molecule in different environment, you will be able to see the color differently. Okay, I have not done anything. The same molecule dissolved in 3 different solvents, exciting at the same wavelength at 400 nanometer. It gives you 3 different colors. Question you can immediately ask, sir, where is the application? So what? The next question should be asked, so what? So what? Well, we can do a lot of things. That's the high-end research. Well, I'll just try to show you, and why it happens. It happens because of this, excited state transfer and how the surrounding dielectric environment can actually induce the electric field onto your molecular dipole. Okay, it's like a more of a dipole-dipole interaction kind of thing. Through this Onsager reaction field, we can try to do. This is the book that you can actually look at, Lakowitz's, principle of fluorescence. Everything you can get it over there. So what happens is this: it goes to the excited state. Now, in the ground state, you have the dipole moment, which is mu g. It goes to the excited state, but through this relaxation, solvent relaxation, it tries to reorient the solvent dipoles around this, and it minimizes the energy. From then, when they come back to the ground state again, give you the fluorescence. Now, this, standard, stabilization becomes different for different solvent dipoles. If the solvent dipole is very high, which is the water, very high dipole moment, they will be doing the process much better way to stabilize the excited state. If it is less polar or smaller dipole moment, it will do a less amount of, and then this gap will be increasing. So what is happening when I'm going from water to my ether? What is happening? This is your lowest gap over here. You go to this butanol, it is little bit higher gap. You go to the even nonpolar, it is even higher gap. And this can be explained by this particular equation. This is called the Lippert-Mataga equation. You can see this delta F is nothing but is all about your dielectric constant and refractive index. And that can explain that why this kind of shift happens, because of the solute-solvent interactions where the solvents having different dipole moments or dielectric constants. This one is clear? All right. So this is what it's all about. What can I utilize? Well, we can utilize, as I was just talking about. Now, this is very easy, but I want to see what is the color it's changing when you're going from this water phase to this cell membrane in the atomic length scale. You change little bit inside and you're trying to see what is the polarity. What is the color of the light is coming out? And that's what we try to do with the same molecule attached with different alkyl chains, okay? And what happens, this is your bilayer structure, lipid bilayers. I hope that everybody heard about that, what is there in our cell membrane. School days, school days we actually learned about this lipid bilayers. Okay, if not, that's what you have to get into more. Okay, and what we can do, we actually because this molecule, just I am showing it over here, that it can give you different colors. Because of this alkyl chain length higher and higher, they can go deeper and deeper inside your water membrane interface. And this interface is only around 15 angstrom. And we actually can scan that water lipid interface with same molecule, what is the polarity. And this is what is your data all about. And from the peak position of these, different molecules, that the fluorescent point is the same, but only I am changing the alkyl chain lengths and putting it below and below and below in the sub-nanometer length scale, and then we are trying to measure it. And from where we can actually utilize this. This is some of the fundamental things that can. So now we know what is the color over here, or over here, or over here, or over here, which is changing only in the 15 angstrom distance. So that color can tell me that. What is the polarity of that interface? Okay. All right. So where to utilize it? One. Well, this is still not yet published. This we are trying to do with ISC Bangalore. Our Dipankar Nandi from biochemistry department. So we have given our molecule to them. Okay. And this molecule seems to be, we can utilize this by looking at the shift of this molecular spectrum. We can look at the antibiotic resistance. And these are some of the data that we have taken a lot of these different antibiotics and put it into this E. coli bacteria. And by the way, this is what happens. The same molecule has been utilized to image. You see, this is your E. coli bacteria untreated. Okay. So my molecule is this, that the two molecules have been used. They go and bind only in the membrane region. Okay. When you treat this one with these, 3 different antibiotics, you can see how the structure of the, E. coli bacteria happens. That's the way we kill the E. coli bacteria. And you can see, ciprofloxacin is the highest one. Fantastic. It really kills up the things. And from this one, we can look at, just by looking at that spectral shift between the two molecules, what is the amount of this peak difference, the peak position of this fluorescence color in the differently treated with different antibiotics. From there, we can say which antibiotic is actually rupturing it more, which antibiotic is not rupturing it more. I am not going to details of this. This is too much of big data set altogether. So the idea is something like this. The two molecules are sitting somewhere here and here. When the antibiotic goes in, there is a thinning of the membrane. Once the thinning membrane is happening, initially when you had the position difference and there is a peak position difference of the fluorescence, when it's thinned out, they come to the same position. You will not be able to observe that particular shift. That by looking at the fluorescence shift, you will be able to capture whether your antibiotics are actually affecting your bacteria or not in the clinical aspects. So this is what the idea is all about. And the last one, okay, I hope I am doing it in the right time, I believe. So again, this is a very, very important field is coming into the picture. Can we make some material which can emit white light for utilization on many of the displays like OLEDs, organic LED TVs, already been there in the market. There are many, many other applications for this kind of. So once you have a, material which can absorb some light, but it can emit all possible colors. White meaning what? It's a mixture of all colors. So right now, can we really make that white color? Because I have shown you at least 3 different colors here, and we can know that if I can have some molecules which I can mix up together, having blue, green, and the red, the primary colors, you should be able to get my white color. Okay, and that's exactly what we have done with these 3 molecules. They are all solubilizing in ethanol or methanol. Okay, this molecule do not really solubilize quite well in the water, so that's why we did not take the water. Now I put up this particular mixture of the 3 molecules, which is having the emission at different position, but will be exciting at the same light. What you can get is a whitish light. So the idea is that, so maybe I can just take out that's one now, and you can see the white light. Now you can actually, by changing the combination of this molecular concentration, you can actually change the scale of the whiteness. There is a scale, whiteness scale, okay? How much white you are having. So you can see, even for a simple molecular solution, you can just mix up 3 different molecules in the same solvent, can excite with the same light, it gives you white light. Because what happens is something like this. This is my mixture emission. It is actually having a very large in the greenish and the reddish region, and that can almost pick up nearly white. You can clearly tell, complain, well, sir, it doesn't have too much of the things over here. So what is white light? Well, that's what you have to really mix up. So can we really mix up the, maybe the 4th one, or maybe you can change the molecular structure a little bit such that it changes the fluorescence position, so that I have a better yield. Now, at least with my eye, I can see that nearly white. Yeah, I am not perfect over there because we just mixed up the 3 samples, and that can give you the white light. And this is what has been utilizing the concept that can we have a material which will, even a solid material, not a liquid like this, solid material, which will actually emit. So all this, quantum dots and their devices can be made nowadays, which can give you this kind of a white light, and which can be utilized for some display somewhere. Because light meaning is somewhere it has to be utilized in display or some kind of a other light devices. So this is what the concept of the ideas that we can get into, even utilizing a simple fluorescence or emission properties. Okay, the same thing can be applied to your nanomaterials like quantum dots, luminescent quantum dots, as Professor Ganguly was talking about, valence band, conduction band. These quantum dots can again, you can excite this quantum dots, the electron will go from the valence band to the conduction band, but when again the electron comes back and recombines with the conduction band, and then they will emit the energy, can give you the light out. Now, can you really make this band gap sufficiently broad enough in some mixture of these kind of particles such that you get a white light coming out of the system? So this is what we can talk about in terms of light and the spectroscopy that we can utilize, not only molecules. I have just talked about everything today about the molecule, but it can be utilized also in the nanomaterials and so on. So for now, I will stop it over here, okay? And maybe the next class will go a little bit deeper inside. What are the things, how we can look at single molecule. We'll talk about that a little bit with this concept of fluorescence. I hope I have kept my time sufficiently. So maybe I can, if there are any questions, I'll be able to share. Okay.
Thank you, sir, for your informative lecture loaded with knowledge. I now request Dr. Amlan Kumar Das to felicitate our speaker, Dr. Soban Sen, sir, with a shawl and a memento.
Thank you, sir. I now invite Professor Ramakant for his lecture on fractal geometry in chemistry.
कहाँ गया? Okay, I'll pass. Okay, for giving me this opportunity as well as Academies to interact with you. And morning, Professor Ganguly, then other speaker, they told you importance of electron, photon, and there was one component also missing electron, holes. Some site is missing electron, that is also called hole. But so chemistry, electron and photon both are very important to do the chemistry. And then question is what we do. And then he also told that electrochemistry, that's going to solve your all energy problem. Interface, how you manipulate. Because in heterogeneous material, why electrochemistry is important? You all like to regulate. पंखे को हल्का करना है, घुमाया, इलेक्ट्रिसिटी से थोड़ा चेंज किया, तेज चला दिया, हल्का चला दिया. Same way we can control kinetics of reaction by turning the electricity. Okay, that's why electrochemistry is important, because you all like to regulate things without putting too many chemicals and all those things. You can control your kinetics through changing the knobs. That's why electrochemistry is important. Another thing is electrochemistry, it gives you opportunity. You make heterogeneous material. So when you call something electrochemistry, there has to be electron, okay, and heterogeneity at which it changes the electron. And another is like reorganization of, there was polar molecules or ions, etc. So electrochemistry controls things by changing electrolyte, dipole of solvent, and the electrode material, and the morphology of the electrode material. And my responsibility is to see that you all get lunch in right time also. So just to check that after to talk you are not very tired, I will ask simple question, because some mathematics very simple. You know the dimension of point or a line or a square, कितना होता है बोलो, जोर से बोलो. नहीं, डायमेंशन 2D होता है स्क्वायर, पॉइंट का क्या होता है 3D, फिर क्यूब का क्या होगा, लाइन, लाइन कैसे 2D, एक पतला सा है. नहीं, ड्रॉन प्लेन का नहीं, उसका तो अब कहाँ ड्रॉ कर रहे हैं, तो सब कुछ 3D में है. ओके, सो लाइन का 1 डायमेंशन, स्क्वायर का 2, क्यूब का 3, पॉइंट का 0. बट देयर इज एक और भी तरीका है केमिस्ट्री करने का और मैनिपुलेट करने का. फ्रैक्शनल डायमेंशन सुना है किसी ने? हाँ, नहीं सुना, पर तुम देख रहे हो हर जगह दिख रहे हैं. जो हमारा ब्रेन है उसका कन्वोल्यूशन, वो एक फ्रैक्शनल डायमेंशन फॉलो करते हैं. सिमिलरली ट्री ब्रांचेस जो है दे फॉलो ए फ्रैक्शनल डायमेंशन. अभी अजीब सा लग रहा होगा, धीरे धीरे यही मुझे बताना है कैसे. एंड डायमेंशन को कैसे केमिस्ट्री में यूज करें कि केमिस्ट्री को अच्छा कर लें. सो ये टॉक उसी के बारे में कि हम फ्रैक्शनल डायमेंशन एक तो पहले बताएंगे कि कैसे फ्रैक्शनल डायमेंशन होता है ऑब्जेक्ट्स के, और उसको केमिस्ट्री को करने के लिए और पर्टिकुलरली इलेक्ट्रोकेमिस्ट्री करने के लिए कैसे यूज कर सकते हैं. एंड दूसरा है कि देयर इज लॉट ऑफ सिमेट्री. यू सी दिस, योर इंस्टीट्यूट इज वेरी ब्यूटीफुल. It has lot of symmetry, lot of beautiful structure around it. So mathematics provides that symmetry. तो कैसे symmetry को use करें to enhance the chemistry. So this talk is about that. So first you are seeing here a temple. Why I am showing temple? 26 January में भी बहुत सारे दिखाए थे झांकियों में. Because it has symmetry, some mathematical symmetry. How you build a complex temple structure? Here is the algorithm. Something ज़्यादा दबा दिया. Okay. Okay. So what we do? We take like a central thing which is larger in length scale. You say make the half of that size and attach in 4 direction of this. Similarly, you make it half and attach in the remaining surfaces. You keep doing this iterative cycle again and again, and end of you will get a very complex looking structure, which a lot of these ancient beautiful temples have. And these kind of, there is like a self-similarity as we go from here. And same self-similarity you see in tree structure. You take a big tree, take a branch, you scale it up, it will look like tree. Nobody will know it if there is no reference point which tells you. And then you cut further branch, you make it, it will also look similar to the same tree. So all these objects which has this kind of different length scale self-similarity, these are called fractal objects, and they follow fractional dimension. This is the key point. किसकी प्रॉब्लम? कौन सा वाला? ये आरो तो आगे पीछे, लेफ्ट राइट, राइट पे, और लैपटॉप का एरो भी मना कर रहा है, ऐसे चलेगा क्या? कुछ चलिए, ये तो एनीवे ऑर्गेनाइजेशन है, तो हो रहा है, ठीक है, चलिए, ठीक है. So there are example here. You see there's this tree, which I mentioned, and then you say thunderbolt. It also very branchy structure. If you cut a small piece of thunderbolt, enlarge it, it will look like whole thunderbolt. Because at many length scale, same structure emerges with some randomness in it. And here also you have a network of rivers. That also, like you have a big broad river, there is a branches. And if you enlarge one branch of the river, you will look similar to the whole river. And you have these glaciers, they have followed similar structures. So all this structure, if some like there's a mathematician, Mandelbrot, who popularized this concept of fractal. He named also and popularized. But we see, okay, 1000-year temple also uses same structure because it is available in the nature itself. All sorts of the natural structure, mountain, tree, cloud, as you can see, clouds are not a sphere. स्कूल में जब सिखाते हैं ड्राइंग करना तो पहले थोड़ा स्फीयर बना के क्लाउड जनरेट करेंगे. माउंटेन्स आर नॉट कोन्स. जब माउंटेन बनाना सिखाते हैं तो एक तरह से कोनिकल स्ट्रक्चर बनाते हैं. कोस्ट लाइन्स आर नॉट सर्किल. ऐसे मैं अनसर्किल करके नहीं कर सकता. पार्क्स आर नॉट स्मूथ. नो डज लाइटनिंग ट्रेवल इन ए स्ट्रेट लाइन. So this is like all these structure which you see all the time in nature. Yesterday there was a lot of thunderbolts. They all had fractal structure. You see all the time tree, they have fractal structure. So how to use this concept of self-similarity, and then question is how to get the dimension. As we all memorize, point is 0 dimension, line is 1, square is 2. But how to get that number is 0, 1 or 2, we will also see that. So this is like there are, if we like how to use mathematics to understand chemistry. There are a lot of mathematicians who built this fractal geometry: Leibniz, Cantor, Hausdorff, Koch, Poincaré, Sierpinski, Weierstrass, Mandelbrot. I will not go into detail of that because that is more mathematics, but we will do more chemistry. But we will take one to name which thing we will use. And we have like similar kind of, if you see this structure, this kind of line in Bhagavad Gita, we say curving back within myself I create again and again. It could be also considered definition of a fractal. As we go along, Koch curve, etc., you will find it's similar thing is happening there also. So this, I have already explained this self-similarity in Templar structure. We go further. But our electrode may look like this. There are a lot of mountains. Just okay, temples in electrochemistry. थोड़ा सा random लगते हैं. If I take my electrode, which we clean usually, in simple case like gold wire or a platinum wire, before doing experiment we clean it. After that we take SAM image of that. We can reconstruct that image by using mixture of knowledge from electrochemistry and the SAM. SAM does not provide z-axis data, okay, that we can acquire through using our mathematical logic. So various things are there. At multi-length scale this is happening, but here it is random. So, so it means if we understand how roughness control chemistry or electrochemistry, we will be able to understand it better than without it. So this is the person whose name comes. There's a beautiful book by him, very colorful books. Anybody should go to library and look for Mandelbrot, fractals. Nice slide, nice picture. You will get convinced that everything in this world is fractal in nature. And he was like a French. Basically, he was born in Poland, went to French for study, and finally worked in America. So it's a kind of multinationality. That's so common in science. You may learn in one country and do research in another country and get a job in third country. If you do well in science, that is possible. And this is like a name after him, Mandelbrot fractal. Here also, if you take what is, you take a small structure of fractal, enlarge it, it will look like same as the whole. Another is, which is we use to introduce the concept of self-similarity and fractal dimension. It's a one Koch, and he's a Swedish mathematician, and he created this kind of structure. So question is, if I ask you, can I pack infinite length thing in a finite dimension, finite object? हो जाएगा? कैसे? हो जाता है? वो भी कुछ ऐसा ही folds बना रहा है, इसीलिए कर पा रहा है. Okay? So it is possible. No, it is not infinite. Some finite into finite, but mathematics can do that. So this is one of those curves. As we go along, you will get convinced. Yeah, we can create. So how to first determine dimension? Because we just memorize point, line, etc. But how you calculate it? This is the way you calculate it. You take, let's scale factor. You take an object, scale it by say factor of 2, and then you see how many this enlarged object equivalent structure can be created in that. So if I take say line segment, double it, and then I will say how scale factor is 2, number of segment equivalent to earlier is 2. And if I take log of k, which is my scale factor, this is the base of log, and the number of that object, that quantity is, gives me the dimension. So like in a line case, this log k of base 2 and 2, it will be 1. So then you, triangle case, if I enlarge it, double it size, there will be 4 possible such triangle in the enlarged state. So again, my scale factor is 2, and the number of segments which I have created is 4. So log 2, and this n is 4. That will be 2 raised to power 2. It will be 2. If I do it with cube, and then enlarge it to the doubles, each side is doubled, the number of segment we can create of cube is 8, and again scale factor is this, log 2, 2 raised to power 3, this will be 3. So this is like a systematic way to create dimension. Now we'll show how fractional dimension emerges. It is clear now how one can figure out dimension in a more systematic way, mathematician way. Not a difficult mathematics, only you have to know how to take log and at different base, which is a scale factor, and how many equivalent segments are created. Okay. So let's do the construction. Cock snowflake. You take a line, okay, of length unity. Unity line. So we are not putting any complication. And then you make 3 equal parts. Then you make 3 equivalent parts, erase the middle one, as you are seeing here. Okay? And then join with equal size segment, these two. This we have erased. So this is my first generation of that, first iteration. Similarly, I take each segment, divide into 3 equal parts, erase the middle one, and join them with this kind of triangle. This is my after second iteration or generation, as we were constructed the temple itself, 1,000 years back. This guy is much younger than that 1,000 years. Okay, and then you keep tracking what is length. This is unit length. This is 4 by 3 because total segments are 4. Earlier there was 3 equal to 1. So it is 4 by 3 length. Then second iteration 4 by 3 square length increases. Then we go to next level. Third iteration. Then it becomes 4 by 3 raised to power 3. And if then you say nth iteration, you have 4 by 3 into n. So length is increasing because 4 by 3 is a large. As you keep increasing power, it will become bigger and bigger. Then you say, what will happen if I do it iteration infinite time? This will have infinite length. We started with a unit length, but final curve has infinite length. So this wonder only mathematics can do. You want to pack in a finite space lot. That's what we do in electrochemistry. We want to make electrode rougher and rougher. Okay, so that we can have more area, because electrochemistry things will be reacting only at the surface. So larger is the surface, more will be the reaction. So this is like a final curve. Again, I know scale factor here was 3, okay, and a number of copies of original is 4. You take again log of base 3 and n is 4. This log gives you 1.261. Is it not wonderful? Like we can get a fractional dimension. This is what we followed same algorithm when we said point, line, etc. Here we say this is the thing. So that's this way you learn why certain object has fractional dimension, because I cannot measure this cock curve, length of this cock curve without using the concept of fractional dimension. Similarly for tree, if I want to know what is the length of all branches of tree, I have to use this kind of power law behavior which has a fractional dimension over it. Same thing happens with our convolution of brain. Each has different fractional dimension. Same thing we see at the electrode surface. We have to capture that fractional dimension to explain the geometry of this complex looking structure. So it means playing with the dimension and the concept of self-similarity, we can change the chemistry. It's okay? Acceptable? Okay. So this is like how we can simulate. And this like behavior is the number of this length goes as epsilon. This is my scale factor when it dh. So, and this is my fractional curve. So again, now you are saying the quote from Bhagavad Gita again, curving back within myself, I create again and again. Definition लगती है ना उसकी तो. But उन्होंने किस context में कहा, one has to understand. Okay. So then question comes कि then you can make various kind of fractal. You can take a sheet, start punching a big hole into it. Then next hole will be half of that in all direction of that. Next will be all keep scale down and you make a kind of Sierpinski carpet kind of. And this is another reflection of fractal concept in mythology or something. You have heard the story of Rakta Bij. Okay? So when Devi kills Rakta Bij, each droplet will become whole Rakta Bij. So same thing happen in fractal. If I take that cock curve, small fragment after infinite generation, enlarge it, it has whole same, it will look similar to what it was earlier. So similarly, a story is in the Rakta Bij, like how to make a story which is big horror story. I have all energy, everything, I keep killing, but more will come, more you kill, more will come. So it's like some kind of notion has been used to give you a real complexity of the problem, ki how difficult it was for Devi to get this. And this is like a picture you can get from there. You can take a small fragment, enlarge it, it will look like whole. So it's like a Rakt Beach kind of dragon looking structure. Okay. So okay, then again come to back to original thing. There are many, you then think of exact self-similarity. All these mathematical type things, exact self-similarity, Koch curve, etc. Then you have quasi-self-similarity. You have some randomness in it. Time ka theek hai? When I have asked him to tell me the time so that none of you miss your lunch. Okay. Then statistical self-similarity. This is like randomness. Randomness is everywhere. Even tree, if you see, they look self-similar but not identical. If I cut the branch, so there is a randomness in all objects. Similarly, electrode also has that part we use, and then there it will be not matching geometry to geometry. Then you will go to something is random, then you talk in terms of mean, variance, or some statistical property. If something is random, you think in terms, even you do experiment, you do 3, 4, 10 times, then you say mean of the value is this, and you put an error bar of standard deviation from both up and down. That way you understand your basic experiment. So when objects are random, it is like that. Professor Ganguly emphasized how to solve energy problem, which this generation is trying to do, that you live on less horrible earth or something like that. उन्होंने बहुत बार बताया कि काफ़ी चीज़ें डूबने वाली है, किसी को बांग्लादेश देखना अभी जाके देख लेना, उसके बाद देखने को नहीं मिलेगा. Okay. So, but electrochemistry से उम्मीद है कुछ हमारी वो प्रॉब्लम सॉल्व कर सकती है. फ्यूल सेल है, इन चीज़ों में क्या चीज़ होती है, किसी भी इलेक्ट्रोकेमिकल डिवाइस में कोई सा भी डिवाइस हो, कहीं पे वो एनर्जी बना रहा है, कहीं पे केमिकल बना रहा है, either it's taking electric energy and converting it to chemical, or it is taking chemical energy, converting it to electricity. That's what electrochemistry does. To achieve that better, you have an interface. You have to make efficient interface by playing with the concept of mathematics or even other way material of that problem. So this is what we have, all these devices, fuel cell, you have supercapacitor, you have batteries which you cannot think of your life. Everybody has wristwatches which has battery. You have your laptop, you have your mobile phone. Without portable battery, you cannot think of that. Even buses in Delhi, a lot of buses, blue color, are all electric buses. So slowly we are trying to reduce pollution and make your life better. Okay. So for that, people do a lot of research, but sometimes you have to do intelligently research. Okay. That's why there is a theoretical electrochemistry which makes you understand, and then say first understand, then do. Lot of time we do, chemists do, make new bond, break new bond. That's what like bond engineering, all chemists do all the time with various chemical, etc. But how to predict a priori? There is like a molecular pollution. You keep making billions and billions of molecules. एक group इधर लगा, एक उधर लगा. Combinatorics, all possibility exists. Only thing is, if we can do intelligently, don't create molecule which will cause cancer, because end of it, any molecule you have to dump on earth only. So only create a molecule which are helpful to us, not the harmful to us. So for that you have to do intelligently, understand before doing. A good experimentalist always do that. First you visualize experiment in mind. अगर उसका अच्छा समझदार है, उसको पता होता है ये होना चाहिए, और उसको experiment वो देखता है, वो that is the true excitement for scientists, because जो वो सोच रहा है वो हो रहा है. Okay, this is like a, people have used this kind of fractal structure in electrochemistry. Initial part, they try to build this kind of design and see whether we can get unique property in electrochemistry. Just several such attempts. Okay, you can make random structure like cauliflower like this. This is just cycling electrode in a solution, sulfuric acid. You can create deposition, dissolution, deposition. You will get this kind of cabbage kind of structure, which is also a fractal structure. Because take a small piece of cabbage, not cabbage, this cauliflower, and then you see it enlarge, it looks like same as whole. So there are various kind of, we keep modifying in a surface with various kind of structure, with substructure in it, nanoscale, sub-nanoscale, all those things to get the certain property, change the property, change the electrochemistry, change the overall output. This kind of various things. So what we do, one thing, just take something. We want to understand randomness there. So one thing, okay, just take some image of it. Some image, if you try to reconstruct height in it, it will be, you will have no scale and lot of noise in it. So you do denoise it, okay. And this is a random fractal structure, so only statistical property have that kind of scaling property. So denoise it, and then after denoise, you might have heard Fourier transform. You take a data, do the fast Fourier transform, take another side of the data, pixels, do Fourier transform. Then average over all of them, okay? Because Fourier transform will give you a complex number. So you take complex conjugate of that number, multiply them together, average over all of them. That quantity is called power spectrum. It gives you like what are various length scale, kitne extent mein uske andar hai. Power spectrum tells you that, okay? And then you can do that power spectrum, you can do cyclic voltammetry measurement if you have neat electrode like put this platinum, gold. You can predict how much microscopic area is there. I know one information, geometric information, microscopic area. So I am taking say SAM image of same electrode, so that microscopic area of this SAM image should be same. By equating this, we can reconstruct the height parameter there. That's what we do, simple idea, but works, very useful for electrochemistry purpose. Because AFM, etc., they don't give you correct depth. They give you envelope surface. Envelope surface is, if I put a bed sheet over these chairs, I will not able to see chair, I will only see the bed sheet ka kahin depression hai, not the depth. So wahi AFM ka problem hai, isliye wo electrochemistry mein quantitatively help nahi kar pata. So you have to go by this. And this is, here you see this is a power spectrum, log scale wave number. If you plot them, these are kind of linear in certain domain. So ye jo hissa hai jahan pe this is indication of it has a power law structure. This is fractal in nature up to certain length scale. And this flicker is the 1 by F noise like power spectrum. So this is where we characterize our electrode. है तो random, दिखता random है. First we say obviously like collection of random temple structure. And you can do a lot of things. You can reconstruct locally by doing this. You do all this kind of, do statistical analysis, distribution, curvature. And whether electrochemistry, there are only few phenomena which happens. Whatever you do, you make sensor, you make battery, you make dye-sensorized solar cell, few things. One is, it always has an electric double layer. What is electric double layer? When you put a metal inside a solution, there is some intrinsic electric field in metal. First, it will capture a layer of solvent around it because they are dipole. So dipole will orient around it. The putting of dipole there, it will change its Fermi level, okay, or the work function of the metal. That's what dipole does. That's why if I do with water, it will give me different electrochemistry. I do same thing with acetonitrile, it will give. As you will see, colors are changing. Same way, electrochemistry changes. Then another thing, some species can go and absorb at the metal surface. Another thing can be, okay, I am doing electron transfer, that species goes and capture electron from bulk species. And then since there is a kind of interface is there is a bulk there, there can be phenomena of diffusion and migration. This is where, until if you start stirring, then it will get hydrodynamic problem also. And since all this electrolyte has finite resistivity or conductivity, there is an ohmic problem always involved in electron. And they have characteristic length scale, they have their influence, what feature of electrode roughness or distances between the electrode will influence your electrochemistry, depends upon length scale, phenomenological length scale and geometric length scale. If they are comparable, they will interact. If they are very wide separated, they will not see each other. Okay? So this is what is all electrochemistry game is about. You do any kind of device making, you will be handling only this parameter there. किसी को एक तो डिवाइस में हमेशा ओमिक रेजिस्टेंस को लोअर करने का टेंडेंसी होता है because if there is ohmic, it suppresses your all kinetics, etc. So one thing in device is always to reduce ohmic. So either you have to put supporting. If it is a solid material, you increase the conductivity. Basically, you have to increase conductivity to reduce Ohm's law के effect. V is equal to IR. R ज़्यादा है, potential drop होगा, I am applying some potential to drive my reaction, but ohmic is smoothing it out, effective potential much lower than what I am applying. So one has to reduce ohmic. And this also comes when I make a deep pores, longer pore, narrow pores, because Ohm's law R resistance equal to rho time L divided by area of that. तो जब area छोटा हो जाता है cross section, resistance बढ़ जाती है. So when I try to enlarge the surface area of my electrode, I tend to make more porous structure. And in that pore, you have large resistance that will also trouble you. So like एक तरफ फायदा भी हो रहा है और साथ साथ नुकसान भी हो रहा है. So whole thing is how to optimize this situation to get the maximum out of it. So वो चाहे मैं super capacitor, whether I'm making a super capacitor or I'm trying to make a battery, both places it comes into picture. So there are kind of various length scale. क्या length scale important है geometry? Atomic length scale is there. When we have metal, there are steps. These steps are random in one edge, and atomic step. So that also influences. That influences processes like electron transfer. That influences the process like adsorption phenomena. And similarly, there are other thing is ruggedness, as we shown you in the first picture there for electrode. That ruggedness can be nanometer length scale. So if it is like about 10 nanometer, then diffusion comes into picture. Below that, it is the ohmic, whatever supporting electrolyte, etc. you add in your system, ohmic will control it also. So that's why you will be able to see through diffusion processes larger roughness, say 10 nanometer onward also. And like this is just mentioned because we are trying to solve this problem using mathematics. So mathematics is also not perfect. Like a lot of mathematics is not developed to handle problem which has so much randomness like porosity and roughness. It's totally random. You would have learned some mathematics, you solve boundary, smooth plane, cylindrical, spherical, but that looks very different. When you have fractal nature, how do you solve? So usually you have approximation method, and then you use physical intuition, which approximation is appropriate. That's why we compare length scales. ये वाला काम करेगा, जबकि ये length scale इससे छोटा होगा, बड़ा होगा, इस तरीके से. There are two methods mathematically which we develop: expansion in local curvature of the electrode, perturbation in surface profile. These two methods solve large quantity of electrode problem. Like in our group, we have contributed maximum to handle the problem with this rough and porous electrode all over the world. I am not talking in. Like we have created 200 equations. Like whole field is developed. All sorts of transient techniques, roughness related, how it influences the electron transfer property, how it influences my electric double layer formation property. All those questions systematically asked, build their mathematics, given a neat equation to explain this. Okay, so this is like, it looks like this. When we make electrode, there will be electric double layer. Everything goes through it. Metal. There is a metal, the top layer of metal is also called gallium. Like there is some spillover electron at the metal. And so if something is spilling out, there will be deficiency below it. So electrons are spilling out, deficiency. That itself make like one place is rich in electron, one is deficient, whole layer of the metal surface. Makes it like a capacitor, electronic capacitor. These things comes into picture when you dealing with the supercapacitor. And then after that, because of electric field coming out of the metal, intrinsic electric field, you have this formation of first dipole layer. And then followed by, if you apply electric field, then it will attract some solvated ion and bring close to it. So electrochemistry is about reorganization of this charged molecule, whether dipole or electrolyte. At the interface, we exploit that property to make like a supercapacitor kind of device. Another is electron transfer. But electron transfer always has to go, because electroactive species has to pass through this double layer region. So it has to, is always coupled with the electric double layer. So that complexity comes. So even if you want to accelerate your electron transfer, this double layer will not allow you to do sometimes. So you have to optimize between double layer and electron transfer to get the lot of properties which you cannot do. So that's what happened. A lot of you would have seen people do, if you are in research, DFT calculation. They do for outside material, but it is not in solution. It is not accounting what will happen in the presence of double layer. That's why a lot of prediction doesn't go. Whatever you predict quantitatively here, you will be lucky when qualitatively it goes correctly. So real system do not behave as we want them to behave until you understand them from all direction also. So like complexity, which we have already mentioned, you can have heterogeneity, you have different crystal planes, you have roughness, you have porosity, you have material which are not identical, you can modify them. So what we are trying to achieve, I'm not going into details because some get little mathematical, but idea to how they look. So overall philosophy is this: you take various spectroscopy to identify, characterize your surface, and you predict what will be my electrochemical responses for charge transfer, charge accumulation, and how if I put a modifying layer over it, how it alters it. That is one thing. So you use theory to connect what we see in AFM and to predict its electrochemistry. हम उल्टा काम भी करते हैं, electrochemistry देख के microscopy करना. मतलब electroscopy will not give you very local detail, it will give you statistical detail about it, because that is what is going into your final response. So we do that also. So it is all about how to predict using this surface property, your electrochemical responses or electrochemical property of that electrode. Other way around, knowing the electrochemical property, can you predict the surface property? Like how much steps are there, step density in a metal surface, that we can do measuring potential of zero charge kind of thing, or electron transfer. Similarly, when we do diffusion, etc., we can predict roughness, say order of 10 nanometer onward. That's what we do here. So they're like, there are people who have tried. Earlier approaches were like equivalent circuit. This, you are familiar with this blind man and elephant story. So the equivalent circuit, still people use it in device analysis, etc. It's like you assume your electrode chemical system is like some electrical circuit. But उसमें क्या होता है, सब कुछ lump हो जाता है certain parameter. So it doesn't give you can fit data, but it will not give you physical insight. सब ऊपर नीचे चलता है, पर काफी लोग use कर रहे हैं because they are resisting to understand electrochemistry. Then there is a scaling approach, but it has some success, some limitation we cannot extend, and it is not very rigorous in origin, it is more physical. So it's some success, some failure. Then people use it like fractional. I have told you fractional dimension. There are fractal derivatives also. That concept also is existing. Instead of you have d by dx or d square by dx square, there can be d alpha by dx alpha. So these things, people use all these tools to understand this complexity of this. But what we call, our approach is ab initio. जैसा दिखता है वैसे ही ले लेते हैं हम उसे. Only thing कि अब मुझे जैसे मैं किसी प्लेन इलेक्ट्रोड की या स्फेरिकल इलेक्ट्रोड का प्रॉब्लम सॉल्व करेंगे, ऐसे ही रफ की चलेंगे, पर उसमें क्या है कि then we have to approximate certain like perturbation, as I mentioned, curvature, expansion, because and if then it depends कि which phenomena I am analyzing. So certain length scale will be smaller, larger. Using that physical intuition, you build this approximate mathematics, and that gives the solution. तो non-stick question सुना होगा सबने, सुना है? BSc chemistry के हैं लोग हैं ना? नॉस तो सुना ही होगा, MSc ने भी सुना है. क्या होता है वो? It connects electrode surface potential to electrode surface concentration of oxidized and reduced species. That's all it does. So if that relative concentration changes, it will change the potential. Or if you change the potential, it will change the rate. So this is valid for reversible electron transfer. Both oxidized, it can go forward and backward. And then you have example like real system like potassium ferrocyanide, ferricyanide. In aqueous system you can take. And sometime when we teach MSc student, we want to show the effect of viscosity, etc. We put glycerol instead along with water. So you make your viscous. Glycerol is very viscous. Okay. Winter में दिल्ली वाले लोग अपने हाथ पैर पे भी लगा लेते हैं, उसे कहते हैं फटता नहीं है. Okay. थोड़ा वहाँ ड्राइव इंटर जहाँ होती है वहाँ लगाते हैं. और दूसरा फेरोसिन, if I want to work in organic solution like acetonitrile etc. Again electrode can be gold, platinum, carbon, plastic, carbon. So this thing we use to analyze our problem. This is our real electrode. ये SAM image से ही निकाला गया. It is not unrealistic. It is no simulation. It is actual platinum surface. Okay, so reversible charge transfer, simple potassium ferrocyanide, ferricyanide or ferrocene into aqueous system. So what we do, earlier theory is by Dijon itself, and what he said, the fractal dimension relates to the flux over these surfaces. Idea is that you measure the how, because dynamic length scale is a diffusion length, which is dt, or d omega by d, or d by omega. Yes, yeah. And with that you correct for that area factor into your equation. You will come with equation where you will get this exponent beta, the current, chronoamperometric current. You are applying a constant potential and measuring current. It scales with the fractal dimension. It has kind of limitation error also we showed in our work, because most of the fractals are not infinite fractal like mathematician Cantor curve. It has finite length. Up to certain length scale it will replicate the structure beyond that. Atom से तो छोटा नहीं कुछ कर सकते ना replicate. Okay. So ऐसे tree का भी structure है, उसका जो smallest branch है उससे छोटा तो नहीं जा सकते. So there is a limitation cut-off length scale. If you account, it be slightly different. So one can do exact mathematics, what we call ab initio. If you have planar, you have this kind of result. The charge transfer current at the electrode proportionate to how many electron transferred per step. Obvious है, common sense है. 2 इलेक्ट्रॉन जाएंगे तो डबल हो जाएगा, 1 जाएगा तो सिंगल रहेगा. और कोई चीज अगर फास्ट डिफ्यूज करके इलेक्ट्रोड तक जा सकती है तो उसके भी प्रोपोर्शनेट होगा. डिफ्यूजन कोएफिशिएंट इज द मेजर ऑफ दैट, हाउ फास्ट थिंग कैन गो रीच. Then concentration of the electrode, which is at the we know Nernst equation controls the potential dependent concentration at the electrode surface, so it is potential dependent. And then you have root pi dt. Dimension of d is centimeter square per second. If you multiply with time, it becomes centimeter. When you square root it, it will become only just centimeter will be remaining. So which is depletion length or diffusion length. If something is getting consumed, it will deplete. So that size is called as with time it increases. So it has to be more depletion. It has to be inversely proportionate. Area of the electrode can be proportional. Larger is the area, more current will be there. So this is like Cottrell equation is called. But when we take power spectrum, it can be written the Cottrell equation portion and the roughness portion. So this structure brings how you can systematically solve. It is like second order perturbation in surface profile, some technical term. It is okay. So it is my job not only to tell you pleasing story, to tell you certain thing तुमको लगे मुझे नहीं समझ आता है, तभी तो इच्छा होगी समझना चाहिए. तो जरूरी वो भी जरूरी होता है ये जानना कि मुझे ये नहीं आता है, because then only you will think मुझे सीखना पड़ेगा. और सीखना पड़ेगा तो इसका मतलब पढ़ना पड़ेगा. पढ़ना पड़ेगा इसका मतलब मोबाइल को थोड़ी देर साइड पे रखना पड़ेगा. आजकल मोबाइल हमारे टाइम में इतना तंग नहीं करता था, आपके टाइम में तो मोबाइल हमेशा लाइफ के अंदर घुसा पड़ा है अच्छे से. ओके, ये हमने एक्सपेरिमेंट भी करते हैं. जब थ्योरी कर ली तो थोड़ा सा ट्राई मार के देखते हैं काम भी कर रही है कि नहीं थ्योरी. ऐसी कुछ नैनो पार्टिकल डिपॉजिट किए गोल्ड के ऊपर, अलग अलग करंट डेंसिटी लगा दिया उसमें डिपॉजिशन के लिए, अलग अलग रफनेस बना देता है. रैंडम रफनेस बनाना बहुत आसान है. देन उसके बाद उसका करंट प्रोफाइल, ये जो लाइन है वो थियोरेटिकल नीचे डॉट डॉट जो है दबे हुए हैं, वो एक्सपेरिमेंटल है. अलग अलग रफनेस फैक्टर का चेक कर लिया, अलग अलग अप्रॉक्सीमेशन में अलग अलग. अब ज़्यादा लार्ज रफनेस है उसके लिए एक अलग अप्रॉक्सीमेशन से थ्योरी बनती है, कम रफनेस है उसके लिए. देन उल्टा काम कर रहे हैं हम, इन्वर्स प्रॉब्लम. इन्वर्स प्रॉब्लम मतलब अक्सर तो हम कहते हैं कि अरे मेरा इलेक्ट्रोड ऐसा है, मुझे बताओ कि इसकी रिस्पॉन्स कैसी होगी. बहुत तरह की रिस्पॉन्स होती है. इलेक्ट्रोकेमिस्ट्री साइक्लिक वोल्टामीट्रिक है, इम्पीडेंस होता है फ्रीक्वेंसी डोमेन में, और टाइम डोमेन में हो गया chronoamperometer. द ह्यूज नंबर ऑफ टेक्निक. So what we have done, we have taken this roughness and developed all those technique की roughness उस टेक्निक पे क्या इम्पैक्ट करती है. So that's why वो 200 नंबर ऑफ इक्वेशन ऐसी इस वजह से आ रहा है. सो अलग अलग केमिकल इलेक्ट्रोकेमिकल कंडीशंस में। सो यहाँ पे हम क्या कर रहे हैं, ये फोटोन नहीं है, ये इनपुट सिनुसॉइडल करंट डाल रहे, पोटेंशियल लगा रहे हैं, और ये आउटपुट करंट निकल रहा है सिनुसॉइडल। ओके, तो व्हेन यू पुट सिनुसॉइडल देयर इज ए आउटपुट करंट विच इज इन फेज विद द इनपुट, वो रियल पार्ट होता है, और एक आउट ऑफ फेज 90 फेज लैग के बाद वो इमेजिनरी पार्ट होता है। इस ढंग से दो कंपोनेंट आते हैं इंफॉर्मेशन इम्पीडेंस करने में। सो वो दोनों ही कंपोनेंट कलेक्ट कर लिए जाते हैं, तो दैट आल्सो गिव्स लॉट ऑफ इंफॉर्मेशन अबाउट व्हाट्स हैपनिंग इन माय सेल। सो उसका एक तरह से इम्पीडेंस रिस्पॉन्स है। फेज बहुत सेंसिटिव होता है, इम्पीडेंस का फेज होता है रेशियो ऑफ दिस टू रियल इमेजिनरी पार्ट एंड देन टेन एक्सेट्रा दैट यू कैन फिगर आउट। दिस इज फेज एंगल, यहाँ पे फ्रीक्वेंसी है लॉग स्केल में। तो अगर इलेक्ट्रोड बिल्कुल स्मूथ होता है तो ऐसी रिस्पॉन्स आती है, एक जगह जाके वो जो ओमिक है वो कंट्रोल करता है, फेज को जीरो कर देता है। रजिस्टर का फेज एंगल 0, कैपेसिटर का 90। ओके, जो डिफ्यूजन होता है उसका आइडल केस में 45 होता है, अगर उसमें एनोमलस डिफ्यूजन होता है तो 45 से ऊपर उठ जाता है। यही है, इसमें यही दिख रहा है कि ये जो हिस्सा है, अगर आइडल स्मूथ सरफेस होती, मर्करी इलेक्ट्रोड ले लूँ, जितनी टेक्स्ट बुक्स में इलेक्ट्रोकेमिस्ट्री लिखी है वो मर्करी इलेक्ट्रोड पे ही काम करती है, सॉलिड पे नहीं करती। ओके, एक्सेप्ट दैट ओके सम कांस्टेंट एरिया इट विल वर्क बिकॉज योर डिफ्यूजन लेंथ इज मच लार्जर और समथिंग दिस कांस्टेंट आर। सो ये जो फेज है, ये जो उड़ गई 45 से ऊपर, दिस इज 45, दिस इज 90, दिस इज 0। सो हियर इट इज रेजिस्टिव एट वेरी हाई फ्रीक्वेंसी, then if we think of idle case it will become 45, but normally solid electrodes are there. If it could have been mercury then it will go like this. If you use a platinum gold or any classic armor it will go like this. ये जो phase 45 से ऊपर उठ रही है because your structure is rough porous, so the depletion length is growing slowly. So in certain thing it is trapped inside those kind of mountain, like bird is trapped inside high mountain, it cannot fly away from that valley. So similarly the diffusing particles are trapped in these cavities, rough cavity, so they're trapped. So it means they will always do the electron transfer, they will be like trapped inside it, so till they do electron transfer they cannot do. So there is an enhancement in this phase, which means enhancement in the current which is coming out because of this roughness, you get higher rate. But there is a one important thing which nobody has done earlier. There is a maximum position in it. Data में दिखता है बहुत clearly. नीचे frequency है, impedance का है. ये जो है, जो उसका RMS roughness है उससे relate करता है. Statistical property. Root mean square roughness mean standard deviation वाला जो concept है, वो roughness मैं निकाल सकता हूँ इससे. और दूसरी ये जो frequency है इसका onset. यहाँ से मैं उसका जो exact electroactive एरिया जो है और माइक्रोस्कोपिक रफनेस फैक्टर वो इस फ्रीक्वेंसी से, ये चीज़ हम फिगर्ड आउट रिसेंटली किया, एंड देन वी काइंड ऑफ दिस इज इसी का लाइक वार्बर्ग यू हैव एक्सप्लेन। यहाँ पे इलेक्ट्रॉन ट्रांसफर ऑनसेट हो रहा है, पहले वो इलेक्ट्रोड सरफेस पे आने के बाद ही वो रिएक्ट करेगा ना, तो उसको फॉर्मेशन में टाइम लगता है, और डबल लेयर फॉर्मेशन का टाइम। तो एक तो ये हो गया RMS, इतना सिंपल इक्वेशन देखिए इससे पहले, नहीं ना, तो नाम से भी सिंपल लग रही है। क्या कह रही है, RMS roughness goes as square root of diffusion coefficient for a given system, we know that information, and जो maximum पे frequency है उसमें कुछ नहीं करना, एक रिकॉर्ड करना है, इम्पीडेंस फेज में लिखना है, ऊपर से उस फ्रीक्वेंसी को करेक्टराइज करना है, डिफ्यूजन कोफिशिएंट इलेक्ट्रोएक्टिव स्पीशीज का पता है, RMS ऐसे निकलती है। उसको अगर हम बाहर निकाल के करेंगे तो वो इन सिटू नहीं है, इलेक्ट्रोड बदल सकता है जब उसका AFM और SAM-WAM करूँगा। तो दिस इज इन सिटू इंफॉर्मेशन विच इज़ वेरी इंपॉर्टेंट टू मेक ऑल डिवाइसेस। इफ आई नो हाउ माई रफनेस इज चेंजिंग ड्यूरिंग माई रिएक्शन, so this we can get. दूसरा ये जो फ्रीक्वेंसी है कैरेक्टरिस्टिक इधर ऑन से, एक इसका ये फैक्टर है जो कि एक स्मूथ केस में आना चाहिए, इसका जो रेशियो है फ्रीक्वेंसी लोअर होती है जैसे जैसे रफनेस बढ़ती है, होल डेटा विल शिफ्ट टुवर्ड लोअर इन ए वेरी दिस फैशन, लीनियर फैशन. So this way you can predict what is my electroactive roughness, and that because roughness जो है electroactive की डिपेंड की आयन का साइज क्या है, जो देखने वाला उस पर डिपेंड कर रही है ना, छोटा आयन है तो उसकी अलग रफनेस देता है, तो ऐसा नहीं मैंने एक जगह निकाल लिया तो that will work for everywhere. इन सिटू करूँगा तो मुझे उस पर्टिकुलर आयन साइज के लिए वो रफनेस जो इफेक्टिव रफनेस फैक्टर है वो मिलेगा. ये थोड़ा सा मैथमेटिक्स से इसको जंप मार सकते हैं। ये भी थोड़ा वी यूज ऑल डिफरेंशियल टोपोलॉजी, इंटीग्रल टोपोलॉजी के कंसेप्ट है, उनको अच्छे से यूज करना आता है मैथमेटिक्स को, तो बहुत रास्ते छोटे हो जाते हैं। ठीक है, ये उन्हीं को रिलेट कर रहा है क्वांटिटी को। तो इस तरह का एक्सपेरिमेंट किया है। ये जो एक्सपेरिमेंट है, मेरी इलेक्ट्रोड सरफेस साफ है कि नहीं उसके लिए होता है। ये प्लेटिनम के इलेक्ट्रोड है, CV है, और ये अलग अलग रफनेस के नैनो पार्टिकल डिपॉजिट किए हैं। एंड देन वी डू द फेज। ओके, सो ये जो डेविएशन आ रहा है, ये 45 लाइन यहाँ कहीं है बीच में, इसके ऊपर ये जो पीक आ रही है, इनको हम निकालते हैं। निकालने के लिए क्या करते हैं, इसी डेटा को डिफ्रेंशिएट कर दिया लॉग स्केल से, तो वो जो पीक्स आ जाएंगे वहाँ से मैं पिक कर सकता हूँ उनकी वैल्यूज आसानी से। क्या वो कई बार पॉइंट फ्लैट्स आ रहा है, पता नहीं लगता ये वाला उठाऊँ ये वाला उठाऊँ, डेरिवेटिव करोगे वो आइसोलेट हो जाते हैं। सो ये कुछ नहीं, सो ये सब डेटा किया है। So how things are getting affected? Why this molecular site should give me different roughness? Because when you have surface like a flat, you can pack some n number of molecule. उसी को मैंने अगर ये convex कर दिया, तो उस पर उससे ज़्यादा molecule pack हो जाते हैं। उसी में मैंने गड्ढा सा बना दिया छोटा सा, कम molecule pack होते हैं। तो roughness से क्या उसका packing density भी बदल रहा है। So all these things has to be accounted when you are trying to understand your data. कि मेरा पैकिंग डेंसिटी बढ़ रहा है घट रहा है, तो काफ़ी प्रॉब्लम उससे ही सॉल्व हो जाती है विदाउट गोइंग इनटू कॉम्प्लिकेशन। एंड ये मेरा एक्सपेरिमेंटल पॉइंट है। रफनेस फैक्टर प्लॉट इधर क्या है, ये ओमेगा, ये लीनियर रिलेशन है विच शोज कि द इलेक्ट्रोएक्टिव रफनेस फैक्टर फॉलोज दिस इक्वेशन एंड विच इज प्योरली डिपेंडेंट ऑन, दिस इज माई कॉन्स्टेंट विच इज 42 किलो हार्ट्स, एंड दिस ओमेगा एच इज किसी भी रियल इलेक्ट्रोड का जो फ्रिक्वेंसी है जहाँ पे वो इन्फ्लेक्शन पॉइंट है, तो उससे मैं रफनेस फैक्टर ऐसे प्रिडिक्ट कर सकता हूँ रियल एक्सपेरिमेंट। ओके, दिस इज लाइक टेबुलेटिंग दैट डेटा वन कैन डिस्कस। So finally, moral of this story, कि we can use mathematical concept of fractional dimension and understand electrochemistry better, and we can use knowledge of our various electrochemical phenomena and can make fundamental equation which are relevant for rough and porous type of electrode system or heterogeneous. We are building for, it's not one day work, almost like 30-year effort. So if you really want to go deep into science, you have to commit for decades. Not for आज एग्जाम पास किया भूल जाओ, नहीं चलेगा। So ये बहुत सारी इक्वेशन है जो नोन है, उन्हीं को हमने पहले जर्नलाइज किया। टेक्स्ट बुक खोलोगे उसमें ये सब नाम दिखेंगे, सैंड इक्वेशन, दिस इक्वेशन, दैट। इसे कि इसका इसी इक्वेशन का इक्विवेलेंट पार्ट रफनेस के लिए क्या होगा, वो क्वेश्चन पोज किया, सॉल्व किया, नई इक्वेशन बन गई। एज ए स्पेशल केस दोज स्मूथ रिस्पॉन्स विल कम आउट ऑफ। So this is cumulative accumulation. There are always some gurus, some students. So everybody has to be acknowledged. You learn somewhere, you teach some people, and you collaborate with people. All these things are there. And some people funds you for your research, and some people appreciate for your research. All those people has to be acknowledged. So this is my cumulative accumulation. So any question or anything, I can stop at this point, I think, from your side. इलेक्ट्रोकेमिस्ट्री ने डरा तो नहीं दिया? भूख तो नहीं लग रही है जोर से? लग रही है, यही असली बात है। ठीक है, थैंक यू all of you for listening.
Thank you, sir, for your helpful lecture. I now request Professor Harlal Singh to felicitate our speaker Ramakant sir with a shawl and memento. Thank you, sir. I now request all of you to join us for lunch to be served in the dining hall. I also request you all to join us for the next session at 2:30 p.m. in the room number 1 of the ABB building. Thank you all.